So good morning. Welcome to the Convergence of Autonomous Systems, AI, and Cybersecurity for National Security and Space. We have a hybrid event today. So we have hundreds of people that are online right now listening in over 35 countries all over the world. And we have a nice packed room right now. I understand that there's been a lot of traffic this morning. So we're expecting some people to come in a little bit late, but we want to get started. So we will get started now. I'm Susan Hutton. I am the Director of Sales and Business Development at IEEE. And I'm here to welcome all of you and to put up our agenda for today, which includes opening remarks from just a few of us. Then we will go to our keynote speaker, Craig Martell, the CTO of Lockheed Martin. And then we were going to have a panel discussion once the keynote is over. And I won't go into everyone on the panel. I'm going to ask them to introduce themselves when we get up on stage. Then we're going to have a lunch. For those of us that are in the room in Palo Alto, we'll have a lunch that will be served outside, and it'll give you a chance to network with everyone that's been in the room. For those of you online, we're just going to leave the session open because after lunch, we have another presentation by Lockheed Martin on space science, instruments and results. And I understand that it's very exciting and interesting. There's a lot of videos. So if you want to come back into the room, for those of you here in Palo Alto and those of you online, come back to the Zoom call and we will start that meeting at 12:30. So with that, I'd like to then a big thank you to our host today, Lockheed Martin. This has been a fantastic event to plan. And I'm looking forward to hearing everybody speak today. And I wanted to thank my partner in crime organizing this event, Mary Snitch. I don't know, Mary, if you want to say anything or just want to stand up so we can thank you.
I always want to say something. But Susan, thank you very much. And if I can just stand here and make very few remarks. We, Lockheed Martin, have been a corporate member of IEEE. We were one of the first ever back in 2018. And over the years, up until the current day, we have truly established a full-fledged partnership that is extremely vibrant. We have received enormous value through our investment over the years in Lockheed Martin. And I would really say, Susan, that today's meeting and our opportunity to host the meeting here at Lockheed is really a sign of that partnership that we have. That is ongoing and again very vibrant. It grows year by year, and we're very, very proud of that. We've got, I have to point out a couple of Lockheed Martin IEEE fellows in the room today, Dr. Mark Mayberry and Dr. Brishan Kingsley, both from the Washington area, both in corporate. IEEE fellows. We have other senior members in the room, and so for my Lockheed Martin colleagues, if you are not yet a IEEE member or would like to know more about it, I'm the person to talk to. And if you are not with Lockheed Martin, but one of our visitors here today, first of all, welcome you. We're delighted to have you here. And go and find Patrick. Patrick is somewhere. My IEEE colleague who can help you with any questions about membership. I think we needed to point out a couple of household items for non-US participants today. You will need an escort to move around in these immediate areas. and myself or a number of my colleagues who are here are available to help make that very easy for you. The last thing that I was asked by our local team here on site is please, if you're taking snapshots with your phone, which I certainly plan to do for posterity, please do not capture the slides on your photos. So I think that is all for me. Shall we turn it over to Tully?
Yes.
Yes, do you want to Tully? Tully Baynard is my boss and the vice president of Lockheed Martin Space Advanced Technology Center and Ignite.
Very good. Thanks, Mary. Thanks, Susan. I'm Tolly Baynard. I'm the site exec for the Bay Area with Lockheed Martin. I also run the research and development for space, one of the 4 business areas for Lockheed Martin. So for those of you here in person, welcome to Palo Alto. As a company, this is one of our research and development laboratories. We've been here almost 70 years now. And we've been doing research and development for space technologies, enabling space to be what it is today, and things that we appreciate related to space. A lot of those things started here in Palo Alto with the research that was done here. So welcome to Palo Alto. For those of you who are online, hopefully you can hear. We do have Jerry from IEEE here on the computer. So if you have questions that you want to ask of the room, she will essentially help interface the people online to the people here in the room related to either the keynote follow-up questions or the panel and panel engagement. So please use that option if you are virtual to be able to get even more value out of this event here. I'll add a couple of extra housekeeping items here. So restrooms were right outside the door here when you came in. If we do have an emergency, go back out the doors that you came in. We do have some security people here. They know the different extra evacuations routes if necessary. So go ahead and follow people in security. Got a security guard here on the back, got a nice badge here on the side. We also have a number of Lockheed Martin employees. They don't have a visitor badge on. That can also be of assistance. If you do need some extra attention, we have a security guard right here at the desk where you came in. Go ahead and just check in with them and they can get you what you need. So again, so welcome. Excited to get into a conversation related to autonomy, AI, the evolution of what are industries. I think there's multiple industries here that are represented, and the future of these industries based on the changes that are taking place related to autonomy, AI, for that. So with that, I'm going to go ahead and introduce Craig Martell. Craig Martell is the new CTO for Lockheed Martin, pushing 100 days or maybe 101 days. We'll see what he corrects. I'm not quite sure. But so slept in what? So Craig joins us with a experience in government and industry, both commercial practices and maybe less commercial practices, like a lot of the Lockheed Martin pieces are not commercial practices. So he's bringing to Lockheed Martin a new view of what we can do, thinking a little bit more broadly about how work is going to be done in the future. And his keynote today will probably touch on some of those ideas. So Craig, thank you very much.
So just before you do that, a little bit of, is it possible for me to walk around in the front? Because if I'm stuck here, then I'll be very boring and I'm more exciting if I'm, okay. Yeah, can I get by? I'm really bad if I just stand still. Okay. So why wouldn't you recommend it? Aren't the mics over there?
There's some there too.
All right, I'll be really loud. Okay, so folks online, can you give a thumbs up if you can hear me okay? I just want to make sure. No reaction, okay. So that might mean they can't hear me okay.
Actually, people are raising their hands.
So
Yes, I can hear you. Yes.
Okay. My name is Craig Martell. I am the 100-day in CTO of Lockheed Martin. Now, that's, first of all, I've decided it's the best job of my career and maybe the best job in the world. My colleagues might disagree with me, but I'm going to stick with that I have the best job at Lockheed Martin. And you're gonna meet Mark later, he's gonna tell you he has the best job. Don't listen to him, it's not true. The reason I have the best job at Lockheed Martin is my job with my team, Mary's part of that team, Chris is part of that team, is to figure out what Lockheed Martin should be 5 years from now and 10 years from now, and make those investments now. So, you know, my immediately prior job, I was the Chief Digital and Artificial Intelligence Officer for the U.S. Department of Defense. I had the privilege of reporting to the Secretary of Defense. An amazing job. However, I felt more grounded after 100 days in the Pentagon than I do at Lockheed Martin after 100 days, because the moving parts are much greater, strangely, than I did in the Pentagon.
Should have been in the Air Force, less grounded.
It looked very good, very good. Mark used to be the chief scientist of the Air Force, so he's the Air Force. All right. Now I joined the Pentagon in 2022. Can someone else tell me what happened in 2022 that has fairly transformed our world? COVID was 2020.
Invasion.
ChatGPT. Invasion of Ukraine, but ChatGPT is what I was going for, given that's probably more salient in the world. Maybe I should have couched that slightly differently. What happened technically in 2022 that had a really big impact? ChatGPT. Now, I've been doing artificial intelligence for well over 30 years. And when I first started, the phrase artificial intelligence was a no-no. Anybody know why you, not you, Mark, don't answer. Anybody know why you couldn't say artificial intelligence 30 years ago? Because nobody would fund it. And nobody would fund it because it failed. It was an AI winter. We had set up a bunch of expectations about what artificial intelligence is going to do, and they didn't deliver. So then we switched to terms like computer vision. Still AI. It's still what we would call AI today, but we called it computer vision so we didn't have to say AI. Or later we called it machine learning so that we didn't have to say AI. So we've come out of an AI winter. We can now say AI again. Unfortunately, we say it way too much. So I'm talking loudly to the room to make sure the folks at home can hear me. So I'm going to start with this question, and hopefully folks online, I will make sure I pause to make sure you guys can try to answer as well. It's a really simple question. What is AI? We're all very smart in this room, right? IEEE.
When a machine can learn to do something via demonstration or some other type of data.
Okay, that's really good. When a machine can learn to do something via demonstration or some other type of data input, you actually answered two different, in my opinion, you gave two different answers. One was learning from data, and one was learning from demonstration. Those are potentially pretty different things. I'm going to, even if you didn't mean it, I'm going to make you say both of them for purposes of the conversation. And I would say that the learning from demonstration is closer to what the hype wants, but further from reality. Anybody else? What is AI?
Non-organic intelligence.
Non-organic intelligence. I don't know you. I'm sure I respect you. So don't take this the wrong way. Not at all. Just not even close. But it's what the hype says. Right? It's really important. I'm distinguishing between the hype, and I'm going to tell you my answer for what I think it actually is, sir. Oh, that's a beautiful one. It's completely wrong, but it's beautiful. He said, simulate human cognition. And that's really, we use the phrase artificial intelligence to, I mean, if you think about the phrase, a synonym of artificial intelligence is simulated cognition, right? Those are synonymous phrases. They're both false. They're both false. In the current, I'm not saying we can't. Don't think I'm saying we can't. I'm saying in the current technology, that's not true. Automation. Beautiful. I can handle that one with no problem. What kind of engineer are you, sir?
Yes.
Okay, cars. Yeah. Great. If you're talking about self-driving cars, I would call that much more robust than just the phrase automation. I'm going to actually talk about self-driving cars in a second. But if it's just automation, then even the page replacement algorithm in your computer is AI. because we automated page. I mean, how many people remember programming we had to do page replacement yourself or memory replacement yourself, right? It's only the gray haired folks. Sorry for you youngins. In the old days, you really had to worry about memory. You don't anymore. You just pretend like it's unlimited. In the old days, you can only do like 640K at a time if you're programming on Windows. So we automated that page replacement, the clock algorithm, which is essentially least recently used twice. That algorithm automated it. I wouldn't call that AI, but maybe I would call that AI. I don't know. Did you raise your hand? Oh, you did. I'm sorry.
I like to raise my hand.
I really do respect you, sir. I'm sorry.
AI is about teaching computers to think, learn, and make decisions.
Did you ask ChatGPT what it is?
And with massive amounts of data. It knows everything.
Okay, so I think the second half of that is right. I think the first half is wrong. And I'll tell you why. I'm going to get, I love this job. I really do. Oh, wait, online? Anybody?
No question, Jeff?
No, what is AI? No answer. Come on, chicken online, folks. Come on in.
It's sampling and tagging data to predict the next possible outcome.
Leave it to an engineer just to ruin the punchline. Sampling and tagging data to think the next possible outcome. We're getting closer.
Looking for patterns and decisions.
Yeah, so looking at patterns, that's 100% true. But there was a book by Duda and Hartz in the late 80s or mid 80s called Pattern Recognition, right? But AI's only been around since 2022, right? Good. All right, can I tell you what I think AI is?
Yes.
Real simply. Statistics at scale. Now, for those of you who know the math of modern artificial intelligence, I know it's multivariate calculus plus linear algebra plus probability plus statistics at scale. But that doesn't flow off the tongue as easily and as nicely as statistics at scale. So the reason I say that last little sentence is in a technical audience one time, I said statistics at scale. And some guy raised his hand and said, that's not true. It includes linear algebra and multivariate calculus. I understand how gradient descent works. Okay, so, but the reason I want you to think about it as statistics at scale is twofold. One, it can actually give you a way to understand what it is. And two, as engineers, you already know how to manage that. Part of the problem with the AI hype is we don't know what to do with it. It comes in at us and it's supposed to be a magic box. And it's supposed to be a box we can apply to this problem and this problem and this problem and this problem and this problem, and all of our problems are solved. That's all BS. None of that is true. And we know that as engineers, we know in our gut that that's just not true. But we're told that it is, we're told we're supposed to implement it, and it's very hard to think about how to manage it. So let me tell you what I mean by statistics at scale. Well, the scale part's clear, the whole internet. Massive amounts of data. Also massive amounts of compute. What do I mean by the statistics part? You gather data from the past to build a model to predict the future. Now, some of you are going, no, duh, and that's the right answer. You gather data from the past to build a model to predict the future. That's all it's doing. Now, what's implied by that? Well, let's talk about gathering data from the past. Well, actually, I'm going to give you an example of what I think is AI and fits that model. Linear regression. Linear regression is AI on that description. And in fact, there are a ton of AI solutions that are just linear regression. And what they do is gather data from the past. They build a linear line. I'm going to be in two spaces. They build a line. You use that line to do interpolation in between the points that were your data, or interpolation outside of the points that were your data. That's it. That line, y equals mx plus b, although we switch it, we say beta 0 plus beta 1 x1, right? And that allows us to generalize it to make it a hyperplane. That line is the model. We built that model using an algorithm. Someone remind me what the algorithm is for linear regression? Sum of least squares. You just find the line that minimizes the errors off the line. That's all we do. Now, is that line truth? No. God, no. Think about the data of linear regression. You would actually fit a curve to it and look like this. Right? You would have overfit to that data. I love talking to engineers because I can go like this and everybody sees that big red scatter plot in their head. You're all seeing that scatter plot in the head when you're watching that red line curve fit or whatever color is in your head. Okay, so it's not correct. The model is not correct. It's statistically correct enough that it gives us answers that are useful. And if we build a model that's linear regression, stick in the linear regression world with me for now, and we build a model that's linear regression, sometimes that line is good enough for the work that we're doing. And sometimes that line is not. And if it's not, what do? Well, we gather different data and we try linear regression again. Or we gather different data and we try a cubic spline. Or we gather different data and we try some other technique until we find a model based upon the data that actually solves our problem. Guys, this is engineering 101. And I want you to think about AI exactly the same way. So you gather data from the past, you build a model, you predict the future. Where can that go wrong? Well, you gather the wrong data. That's one way it can go wrong. You build a distribution. Great. Does that distribution describe where you're going to deploy it? I don't know. You got to test it. You got to find out. Sometimes it solves the problem where you're deploying it. Sometimes it doesn't. Another thing that can happen, you gather data from the past, you build a model, you predict the future. It actually works. Then the world changes. Now, disruption. A disruptor. A disruption. So I'll give you an example. A couple of jobs ago, I was the head of machine learning for Lyft. And I took that job in March of 2020. What happened in March of 2020? COVID. So the person who said the first time, they finally got sick. In March of 2020, I had one interview in person. And for those of you who've done a Silicon Valley interview, that was like 10 hours long. So I did that one 10-hour long interview in person. For those of you who haven't, you sit in a room and then they just sort of parade in, beat the heck out of you, and then tell you got the job or not. It's a joyous experience, isn't it? All right. So I did that one interview, and then for the rest of it, I was at home. And think about the number of models for something like rideshare, pricing, supply and demand, matching. Now, just for those of you who are interested, the matching algorithms are really fascinating because it is reinforcement learning across the whole town, across the whole day. Really fascinating. So it's not just a map, it's a tensor of maps. And it's really fascinating because this person here might want to end up at home over here at the end of the day, but I might need that person here at 2 a.m. because that's when the bars get, or there's a concert at the amphitheater, right? And if that's the case, then I know this person's willing to work late, but this person's not. And this person's further away than the rider over here. So I'm going to match them with this driver because I need this driver over here. So if anybody knows how AlphaGo worked, and now we can talk about it, we did something very analogous for the whole board, the whole map set over time for the whole town. Really fascinating work. So all of those models depended upon some stationarity in the distributions, right? The distribution stayed roughly the same. COVID hits. The distributions collapse. Nobody wants to drive. Nobody's taking a ride. From a profit perspective, pricing had to change drastically because I had to lure you to take a ride. If I was charging you the $35 I wanted to charge you, you wouldn't do it. If I charged you $7, you did it, right? So we had to radically change all of those things. So one of the first things I did when I got there is take a look at how recent the models were retrained. And it turned out that over 35% of the models haven't been retrained in over a year. So we were running a business on models that were trained on data that was really effective data, gather data from the past, build a model, predict the future. It was doing that until COVID hit. So then you have to gather new data and build a different model because the world can change. Distributions are not stationary. That's stationary. Right? Yeah. Distributions are not stationary. And even if you gathered the right data the first time, it's not guaranteed to be the right data. Okay, AI, gathering data from the past, build a model to predict the future. Let's talk about ChatGPT. How many people use ChatGPT in their daily workout? What do you use this? No, you.
Yeah, learning the new how technology works.
Learning new technology term. I think that's a great use.
I am an engineer, but now I do recruiting. I use it to help me prep candidates, interview candidates, prepare them to meet their plan.
Great.
Efficiency, right?
But give me an example of
Just like you said, like a job listing, right? Rate me that job list, right? That summarize meeting notes, right?
So in most of these use cases, the ability to determine when it's wrong is really up to you. You read it, you say, did it work well for me or not? And if it didn't work well, you would just hang on to ChatGPT for a second, and let's switch to self-driving cars. I have two self-driving cars. I have one here in California, one in Washington. The one here is a Mustang Mach-E, and if you've not used Blue Cruise, it's Ford Blue Cruise. It's really, really good. And the one in Washington State is BMW i5. Now, what's really interesting is the training data, because Ford training data was trained on Ford drivers, and it's a very polite lane changer. BMW training data was trained on BMW drivers, and it drives like a BMW driver. It goes, like it snaps your neck when it changes lanes. And the Ford goes really polite. So training data, remember, gathering data from the past. Well, you got to sample your data correctly, and if you're going to, maybe it's right though. Maybe a BMW owner is going to want its self-driving car to drive like normal BMW drivers.
Not 4 a.m. a Sunday morning going to Logan.
Probably not a good idea.
Not a good time.
Makes you sick to your stomach.
Yeah.
All right. What's fascinating about self-driving car? Let's think about it. Or even if you don't have a self-driving car, just think about adaptive cruise. Okay? So the beauty of adaptive cruise for lane keep assist is you're driving down. I don't have to keep adjusting the speed. It does it for me. It's completely gathered data from the past. It's built a very, very, very complex model, with billions of parameters probably. By the way, everybody know that if you have a self-driving car, you have a dedicated chip in your trunk. That's where it is. In the sidewall of your trunk is a little suitcase size, the briefcase size thing, which NVIDIA sells, which functionally driving the car. If the system gets it wrong, the cognitive load to tell when the system got it wrong is very low. The car in front of you just gets too close to your cover. Now, if you fall asleep, that's on you. Let's assume you're doing your job and staying awake. You get the car in front of you just gets too close to your comfort, and there's a really easy escape hatch. What's the escape hatch? Hey, this guy, as I'm getting too close to the car in front of me. To the brakes. Something you all know how to do. If with lane keep assist or with the self-driving car, it gets a little too close to the truck next to me. What's the escape hatch? What do? Just turn the steering wheel. Just adjust it. Now, I don't like the fact that the fight's back against me. Should work on that. It should tell almost immediately that I'm trying to override and not fight back against California. But regardless, it's a very easy escape hatch. Now let's talk about ChatGPT. Or, sorry, I don't need to pick on OpenAI. Any large language. By the way, large language models have been around since the 50s. Language models are not new. They're not new at all. The only difference is they got big. And by big, I mean massive. Massive amounts of data and massive numbers of parameters. But language models have been around, when was AT&T doing, or SRI, or
50s was the first
Yeah.
conference, but we had 100,000 new vocabularies.
Yeah, so they've been around for a really long time. Like, you didn't know it because a small language model, by small I mean 100,000 parameters versus billions of parameters. A small language model isn't as effective. All right. If you give it 10 documents and you say summarize this for me, these are the promises, right? The promises aren't just first draft generation. First draft generation I'm on board with. Why? The escape hatch is you. You read it and you say, I need to write something that represents me. My reputation's on the line. If it's wrong, I'm in trouble. So I'm gonna rewrite it the way I so I can guarantee it's quality. Right? Coding. I'm not bothered by coding. Why am I not bothered by coding? Because the code has to compile. Secondly, if you're doing it right, you know, we all work in some companies where we're not, but if you're doing it, not Mark. If you're doing it right, then there are integration tests, and that code has to pass those integration tests, and there are penetration tests, and the code has to pass that. So I'm not that bothered by code generation because there's an external ecosystem that validates the output of the model. But now, I ask it a question about some new scientific topic, and it gives me a long answer. What's the cognitive load to know when it's wrong? Think about that while I remind you of something. What I said was, it's statistics at scale. We gather data from the past, pick the model of the future. It is guaranteed to be sometimes wrong. Because I use the phrase statistics at scale to assume a probability less than 1. The probability of 1, then I'm going to call that a deterministic system. Okay? So it is guaranteed to be sometimes wrong. Guaranteed to be sometimes wrong. What do we call it when a large language model is wrong? Hallucination, a word I hate. And the reason I hate that, here's why I hate that word. I hate that word because it assumes a cognitive being gone awry. It assumes cognition that got it wrong. There is no cognition. It is simply a statistical system. I can prove it to you mathematically, I promise. It's just a collection of logistic regression. And for those of you who really know it, not all activation functions are logistic regression. I know that, but it's a better story. So it's a collection of logistic regressions. There is no cognition. You don't put a bunch of logistic regressions together and get magic. It's just not how the world works. So there's no magic, there's no cognition. It's a statistical system. At the end, it's a softmax over all the things you want to predict. So it's just a distribution over all the things you want to predict. And it predicts the next most likely thing. So it's guaranteed to be sometime wrong. So you feed it 10 documents and it gives you a summary. What's the cognitive load to tell when that's wrong?
You have to read all 10 documents and know exactly what they meant.
Read all 10 documents. So the cognitive load for the use cases that many people want to use this technology for is massive. There's no easy way to tell when the system gets it wrong. Now, do we care about that? In some use cases, not at all. In some use cases, very much. And this is my fundamental problem with the hype. I've been doing natural language processing my entire career. I have never been more excited than I am right now. These systems can do natural language processing so much better than anything the field has come up with. But they do it in such a way where it speaks authoritatively, it speaks fluently, and we as humans, I'll explain why in a second, we as humans take that as ground truth. And there's very, very few ways to tell when the system is wrong. Particularly, and here's where people want these systems. People want these systems so that they don't have to pay experts anymore. They can hire novices and the system and save a bunch of money. The experts can tell when the system's wrong. The novices cannot. So you ask it a new technical question, you don't actually know if you're getting the truth. Now, let's say it's wrong. So a paper I read about a year and a half ago, which is way outdated, said it was wrong 17 to 30% of the time based upon the topic. Okay, so 17% of the sentences to 30% of the sentences were incorrect. Now, let's say we've gotten massively better. Let's say we have that, and we're down to 8.5 to 15%. Or let's say we quartered that, and we're down to 4.25 and 7.5%. So 4.5% of the time, 4.25% of the time, it's wrong. How do you know? How do you know what 4.25% is wrong? Could it be? So I'll give Chris. What was the example? Was it you? You gave me an example the other day where you asked it. It told you something was somewhere, but it was somewhere else.
Phoenix was in Pacific, like daylight.
Oh yeah, he asked what the time zone was for Phoenix. Because we were in Phoenix yesterday or 2 days ago. Remember we were there on the cover. We were in Phoenix yesterday, and it said Phoenix was in Mountain Zone. Mountain time. Now that's a small mistake, unless you're planning some operations that require coordination. Those of you who don't know, Phoenix is Pacific time. So something as simple as what time zone Phoenix is in, it just simply got wrong. Now, why does it get it wrong? What's my time? How am I doing on time? Do I have to stop soon?
15 minutes.
50 minutes? Great. Oh, I heard what I wanted to hear. You got all day. Just keep going. All right. So why did it get it wrong? Because what do these systems do? Let's talk about what this does. What does a language model do? A language model predicts the next word. Let's generalize that. The next token based upon the prior token. That's all it does. In the old days, it says, what's the probability of word n given word 1 to n minus 1? It's a very big conditional probability table. Still a language model. It's a very big conditional probability. I love talking to engineering because but now it does the same thing. You give it the prior words, and the prior words are your prompt, and anything hidden in there. So it has all these prior words, the prompt, and it simply predicts the next token. It does not predict an answer. It predicts a token. Or for the ones that draw pictures, it predicts a pixel. It predicts one pixel or one token. And then that pixel and that token become part of the context. And then it predicts the next token. And the next token. And the next token. Now, it pauses, gathers all those tokens up, and spits it out to you as if it's generating an answer as a whole, but it's not. It's doing it token by token by token by token by token. And so sometimes the next most likely token in its distribution, its model, created by the data that you gathered, sometimes the next most likely token is mountain and not Pacific. It doesn't know that Phoenix is actually in Pacific time zone. It knows nothing about the world. It's only strings. And it simply predicts the next most likely token. Now we call that hallucination. I call that an error. I hate the term hallucination. It's an error for that use case. So let me leave you with this as engineers. These are statistical systems. You know how to manage statistical systems. You work with them all the time. You build them all the time. It's simply a statistical system. It gathers data from the past, it builds a model, it predicts the future. Now, remember earlier I asked you, I said one of the mistakes you can make is to gather the wrong data. For many, many of your problems that you have to solve, do you believe the entirety of the internet is the right data to solve that problem? Right. Why would you believe that? The signal-to-noise ratio would be remarkably low, right? The SNR beyond would be infinitesimally small because you have the entire internet and you have some small, like 40 pages of that internet, which are the signal that you need, and the rest of it will swamp it out. So the signal-to-noise ratio would be minuscule. So why would you build a model where you gather data from the whole world to solve a particular problem? I want you to think about these things as engineered systems. What's the data you need to solve your problem? Now, there are some nice tricks. When you do distillation, what you're telling the model to do is project into a smaller space that's about these things I care about. That could work. That's interesting. That's an interesting trick. You have the entire space of the topics of the internet, and you feed it some specific documents. It tends to focus on that space around that topic. So that might work. Notice what I said. That might work. You gather data to solve your problem. You can try one of those big models, but if that doesn't work, just use linear regression or something else. Like, don't stop thinking this is the only path. But you could try a distillation. You could try, because these tools really do some things amazing, right? But simultaneously, figure out how to measure your problem. Figure out how to measure whether it works. Just stop giving up being an engineer. You have to gather data. You have to see if it solves a problem. And you have to you have a problem. You gather data to solve that problem, and you have some measurement to decide whether that problem is getting solved. Straightforward engineering 101. Keep doing that. Do not believe this is a magic box that can solve everything you do. That is not. It's simply a very large statistical model that's guaranteed to sometimes wrong. With very few easy to use statements. Okay, I'll pause there. Thanks.
Take some
I
questions.
sure will, but I would say one more thing, because I can see my teammates looking at me. Can we just change the slide with us? Okay, we spend a great deal of energy at Lockheed Martin figuring out exactly what I just said. What's the right data to solve the problems? And we spend an amazing amount of time figuring out how to measure correctness. Because in Silicon Valley, a 70% solution can make you billions of dollars. In our world, a 70% solution, people die. So we spend a great deal of time gathering the right data, defining the problem, and making sure we know how to evaluate it and test it after we get it right. And there are lots of folks in the room who know better than I do all of these things that we do, and we're happy to talk about what we do. Okay, questions?
Can you give your opinion on agentic AI?
Sure. It's what's the question? Oh, sorry. Can you give your opinion on agentic AI? Okay. It's a collection of gathering the data from the past to build a model to predict the future rather than an API.
But are these models more domain specific and therefore have
It's up to you.
probability?
There's no magic here. Some engineer builds a model by gathering data from the past to build a model to predict the future and wrap it in an API. That's agentic AI. You've got a bunch of these things. Some are smaller than others, some bigger than others. So we spend all of our energy talking about the infrastructure, was it MVP, whatever the infrastructure for agentic AI. We spend all of our energy talking about that as if that's going to solve something. That doesn't solve a thing. It just makes it easier to hook up the APIs and to pass input and get output. But we've been doing that for forever, right? Like maybe not since Babbage, maybe not since the EI, but since the internet, right? Since RPC, right? So we've been doing RPC for a really, 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 really long time. The only difference is everything I just said is now there's a collection of them put behind APIs. So whether sewing those together is magically going to create a good answer, absolutely not. In fact, it's harder to test. So my concern with agentic AI is my concern with regular AI. Make sure you have evaluation criteria. Now, you should do evaluation criteria for each of the APIs, and then you should do evaluation criteria for the system as a whole. However, we've all been doing system of systems for a really long time. We know how to do that. Really nothing new here, except for the fact that maybe the types of APIs that are being, the types of functions that are wrapped in API. So I really mean this on purpose. I want to de-hype all of this. There's nothing magic. If that set of 10 models are all really good, and they've all been validated against data for their specific use cases, then maybe you can build a system of systems that works great. If you think we could just, if one thinks we could just take a bunch of download from Microsoft and from Anthropic and from take another one, Mistral, and wrap them up in an API and suddenly get intelligence. You weren't listening. I'm not saying that to you. Ready? You just tell me for me.
So if AI is a such statistical system, how can we trust it in a real-time environment? What point of time we can say that this we can use it for two, right? There is no way, right?
No, not true at all. Not true at all. Not true at all. That would be your product management job, by the way. And so here's what I mean by that. One should use AI. I got this from Cassie Kershaw. Is that how you pronounce the last name? She used to be the first chief decision scientist at Google. One of the smartest people I know. And she said this really beautiful thing. And I always want to give her credit for it because it's really elegant. You use AI when one, you don't care about errors. I'll give you an example of that in a second. Or two, errors are easy to detect and correct. That's when you should use AI. So when do you not care about errors? Well, my wife, we moved to Seattle from here. We kept our place here, but we moved to Seattle in 2018 because I wanted to stay married. What do I mean by that? My wife got this amazing job at Amazon, and we were going to go to Amazon. Right? And so Amazon makes an unbelievable amount of money in recommendation. What do you think the success rate in recommendation? Ridiculously low. I don't know. I really don't know the answer. Let's call it 5% or 30%. You just don't care about errors at all there because that 5% makes you hundreds of billions of dollars. There's an example where you're perfectly okay with errors. Check. Another example where you're really okay with errors is Google Ads. You think Google cares that you don't like that ad? Not at all. What they care about is you still search, you still look at the ads, and enough of the people click on it. They don't even have to buy anything. You just have to click on it. And Google makes massive amounts of money. Right? So there are plenty of examples where you use a statistical system where you don't care about errors. Okay? There are other examples where you use a statistical system where errors are easy to detect and correct. I gave you an example, ADAS. We can self-driving cars. It's low cost, excuse me. The human cognitive load to determine whether the car gets it wrong. They don't promise it's right all the time. I mean, no one talks about level 5. They don't. I think most people have forgotten those phrases actually. Maybe you do internally. It's not a selling point anymore. If it gets it wrong, you just correct it. But most of the time, you're cool with it. So what you sit down as a product manager, I said a product manager, is you'll say, what kinds of errors will my customers accept? Will they accept false positives? Will they accept false negatives? So false positive is when I say something is, but it's not. And a false negative is when I say, no, it's not, when it really is. Okay? So will they accept false positive? Will they accept false negative? How about search? Search is a great example. You don't actually care about the false negative. What are the false negatives? A whole bunch of relevant documents that didn't get shown to you. Those are the false negatives. You don't actually care about them. You only really care about the false positives. What are those? Somewhere in the top 10, because let's be honest, nobody looks past 10 blue links. I don't even scroll up.
They won't be able to get more about
it. They can't scroll? All right. I think that's fine.
the number 7%. Go ahead.
All right. So you get 10 blue links. All you care about is that at least 7 of them are relevant. Right? So you're okay with called precision at 10. You're okay with precision at 10 being 70%. So there's a 30% error. Never mind the fact that there were probably hundreds of millions of documents that were relevant that they didn't show you. You're totally okay with that. So there are plenty of use cases where statistical systems are very valuable to your customer and make billions of dollars. They don't have to be perfect. You have to think really hard. The statistical system, you guys are engineers, remember? I'm assuming you're all IEEE. So this statistical system, what are the possible errors the system can make? Can I mitigate against those errors? And if I can't, are they acceptable to the customer in the deployed situation? These are just straightforward engineering questions you have to ask. He was next, then you, and then we're going to check on that.
My final question is, are these systems truly scale? One of the things you're really encountering with a lot of them is the energy. Are there scaling limits? Particularly, a lot of them are now trying to gear toward artificial general intelligence. Is it an oxymoron to really call these things scalable?
Well, so that's a great question. The whole scaling law story bothered me from the beginning. So a friend of mine, Gary Marcus, has spent many Substack article about how scaling is it's like Moore's law. It's a generalization. It's actually not scaling laws are not laws, right? And we already reached the limits of scaling in lots of things. I just read today that potentially 50% of the content on the internet is being generated by AI. So you're going to reach a fixed point there where it's just noise, right? But I agree with you. I actually think if we're going to move forward, and Lockheed spends a lot of time thinking. So my warnings are not to say don't do it. My warnings are to say think carefully about it. I want to be clear about that because we think we work really hard at this. We've got to find a way for models to get smaller. That's actually less relevant, but correlated. We have to find a way for compute to go down. We have to find a way for compute to go down. I've seen some startups really fascinating analog chips where the actual network is captured in the resistance on the chips, and they're slightly slower, but so that the coefficients of the network are in the resistance on the chips. Really fascinating, and the power level is massive. The whole chip is smaller, and the power level is small. So I think we're really excited about that direction. I said one other person, then online. You and then online.
Nobody online.
Nobody online. Great, well, then you.
This falls from that question. SLMs are the future, or like Don McCool says, all that is going to get us where we need to be. Touching on how.
Well, what do you mean? What? Jan LeCun's saying something very specific. Jan LeCun's trying to recreate cognition when he says this statement. Really bad at it. I like him a lot. And I think his architecture for that looks really promising. It's a good hypothesis to test it. But SLMs aren't trying to get to that. SLMs are trying to solve. Be an engineer for a second. Don't be a cognitive scientist. Be an engineer. You're going to be a cognitive scientist. I fundamentally believe we're going down the wrong path. We can have that conversation over coffee. If you're going to be an engineer, these things work in some use cases. They don't work in other use cases. So some use cases, SLMs will work great. In other use cases, small language models. By the way, they don't really mean small. They mean big, but not as big. Still massive, but not as massive. But so really, you got to get clear on the use case, and then you have to ask what technology is going to solve my use case. If your use case is recreating human cognition, join a philosophy club. That's really my theory. And we have to think different. But if it's to solve a particular problem, maybe that's not the way. Does that make sense? Short answer. Right? The whole message here is be an engineer, right? That's the whole message.
So Ray Kurzweil has become famous for predicting the singularity.
He's also become famous for never dying.
Which means, to me, we'll have cognitive AI. Do you believe we'll ever have cognitive AI? And if so, how soon?
Well, if I knew the answer to that, I would keep it as Lockheed Martin proprietary secret. Because we wouldn't want our adversaries to get it. The answer is, I don't think we're going in the right path for that. I fundamentally don't believe that a statistical system is equivalent to the brain. And I think it's a fundamental mistake. And I'll leave you with this philosophical thought, which I did not make up. I got from John Searle, a philosopher emeritus. There's a fundamental difference between simulated and artificial. Artificial intelligence shouldn't be called artificial intelligence, it's called simulated. And there's a fundamental difference. I'll give you an example. I had open heart surgery, my nostril valve broke. I didn't eat too much fat, congenital. So I had open heart surgery. And during the open heart surgery, they pumped my blood through something called an artificial heart. So what does an artificial heart do? It does all of the functions of a heart, or I would have died. Now imagine they pumped my blood to a simulated heart. What would happen? You die. I die. In fact, the screen would just get wet. Right? With my blood. So just because we can simulate behavior that makes us think cognition's happening, doesn't mean we've artificially built the precursors necessary for cognition. So in my view, again, John Searle, I really want to be clear about where I get these ideas from, is if we want to create true artificial intelligence, we first have to understand the brain. Why? Because everything that we call intelligent has a brain. Lizards are intelligent, they have a brain to some degree. I mean, they have a brain, they're intelligent to some. Cats are intelligent. They have a brain. Some people call dogs intelligent. They have a brain. I didn't expect any dog owners to say that was my goal. So my point is separate simulated from artificial. Right now we have simulated, we have an approximation of simulated intelligence. I don't believe that's the path to creating cognitive artificial beings. Can we create cognitive artificial beings? Dude, if I knew that, I wouldn't tell you I would invest like crazy. I don't know. But if we can, then it's probably looking at brain science and not looking at, look, guys, what is, people get so excited about GPUs, and I know they're making a lot of money. That's awesome. But it's just doing matrix multiplication. Do you really believe that a bunch of matrix multiplication gives you the spark of life? Like, that's a bizarre view to me. Just really, really, really fast matrix multiplication, and you have intelligence. That just seems so bizarre that we would think about that. There's no magic in the chip. It's just doing matrix multiplication. It's doing vector calculus. That's it. At scale, really fast, so it fools it. And it turns out we're easily fooled. Online?
Yes.
Online has to win.
Online has to ask. What problems do you need your supply chain to solve to support Lockheed's objectives?
Oh, very different question.
Yeah, I know.
That's a more complex question, and I feel less. Only being 100 days in, I feel less qualified to answer that. I think that's a great question for Mark.
Yeah.
I think it's a great question for Mark during the panel.
Okay.
So I'm going to punt that to the panel.
I will hang on to it for the panel.
Because I don't know yet.
Yeah.
I mean, I have some ideas, but we're going to need chips.
Yeah.
Right? How many chips and of what type? And how many of those chips are easily solved by the supply chain versus have to be made specifically by us under specific regulations so that they're only for military use? These are the things we have to figure out.
Just going to your comments about cognition, and I guess I kind of want to counterpoint a little bit in that I think that we talk about as cognition is really pattern recognition. Our brains are pattern recognition as well, right? We recognize that it's daytime. We recognize that there's another human. We recognize, when our stomach says we're hungry. I mean, everything is inputs that we've learned.
No, in fact, we don't even recognize. I'll give you an example. We don't even recognize it. You're walking. Let's say you're walking in the path up towards behind Stanford, up that hill. You're walking on that path, and you step on a stick that rustles the grass next to you. You jump back in the air. You realize, why am I jumping? That was just a stick. Because your brain thought it was the same, and your brain jumped before your cognition even realized. So we don't even always recognize it. In fact, when you drive, most of us don't pay attention anymore, and that's a good thing. You drive. Think about walking. When you walk, you don't think about walking. You can walk upstairs. You can step on this thing and you adjust. You do many things where your body recognizes patterns.
Well, we had to learn to walk.
Don't go through cognition. I agree. So I'm saying pattern recognition is a big part, but there's much more. I don't think it's just pattern recognition. And here's my example of that. This is a philosophy class now. We just switched to philosophy. Yep. You're saying a sentence, and particularly if you've ever been in public speaking, I've done it 7 times since I've been up here. You're saying a sentence. Halfway through that sentence, you realize, oh, that's not really, where that sentence is going is not really what I want to say. So you actually change it halfway through. So there's a distinction between the pattern recognition and generation and something like semantics about the world. You have a view of what it is that you want. So we do have some sort of internal representation of the world that is distinct from just pattern recognition. Now, it might have generated that pattern recognition, but it doesn't matter. It's still something robust. That's what, if I say a sentence that's false, you have some notion of truth or falsity that's independent of just the pattern. So it's not just pattern recognition, it's much more complex. We have one more question. He's already asked, so I'll give it to him unless someone else has. Sorry, man, you lost.
So you are talking about that vision of like the correcting the sentence. I would argue that it's just a context window of LLMs, like that.
Yeah, I just don't believe you believe that, and I challenge you to go home and think about it. Don't get enamored by the current sexiness. This has happened throughout all time. So people used to, when the most complex technology were clocks, people called the brain clockwork. And they argued that we work like clocks. When the most complex technology were Winchester drives, for those of you who remember, we all said things like, oh, my CPU is overwhelmed or it doesn't fit in my hard drive. And we described our brain using that. Now we're describing our brain using cognition using large language models. Don't get enamored by the current most sexy technology and most complex technology and think that's the way the brain works. None of us in this room, unless you're a neuroscientist, know how the brain works. And we shouldn't be using these metaphors that we use to describe systems that are already too complex for us to understand. We use these metaphors to describe systems. That doesn't mean that's the way the brain works. So I challenge you to challenge yourself. Happy to be wrong. I am happy if it turns out we are a large language model, I'll be shocked, but it might be true. But let's do that empirically. Let's actually do some studies and let's fund the brain scientists to figure it out, not the engineers in the show. There was only one more question, dude. So, I go for it fast.
Pretty quick. I mean,
Pretty quick. I said fast. He said pretty quick.
unless there is feedback, cognition and cognitive errors. I'll give a good example. I worked in travel industry. We could predict light spots kind of reconnecting. When the recent air traffic control kind of went body, we assume that everybody will be there at the same airport and Newark and things like that, but Newark to actually manage the flights for 5 hours a day. You cannot kind of recognize it. There's a
I think that's an excellent point. Again, I would punt that to the cognitive scientists and the brain scientists. That's not an engineer's job. But I got to be done. I'm so appreciative of your time. Thank you very much.
Thank you. That was wonderful. I am not an engineer, and I was so interested I could listen for another hour.
What's AI? What's AI? Somebody tell him. Statistics at scale. There you go.
I have a degree in computer science, but when I took computer science, I wrote applications in Fortran. So now you know how old I am. I don't know if half of you probably don't even know what that is.
No, I think most of them are having flashbacks. Horrible experience about Fortran and yes.
Okay, we're not going to take a formal break, but we do have to bring the panelists up to the stage for our next panel discussion. I'll remind everybody there is coffee outside, so if you want to go grab a coffee or something, you can come right back because we're going to start in a minute or two. And thank you very much.
Good. So
I just
you,
keep
We'll turn them on.
Oh, you're gonna turn them up. Thank you.
Okay, we're back. And before
we are on.
we're back, okay. Before we begin our panel discussion, I'd like to ask the panelists just to introduce themselves, tell us a little bit about themselves and what they're doing and working within AI and why they're here today.
Thanks, Susan. Dr. Mark Maybury. I'm just actually looking at this beautiful art. Apologize for people who aren't here physically in the room, but actually magnificent. Actually, a combination of sensing and human art in space. I'm the former. Oh, louder. Sorry. Good morning, everyone. Dr. Mark Maybury. I'm the Vice President of Commercialization here at Lockheed Martin, which means I bring in large tech and tech companies and small tech companies to our businesses, but also spin out technology. I sit on the board of 2 subsidiaries at Lockheed Martin, Ford Adjacent, which is a fabless design company, sells to commercial and in defense, and also Astris AI, which is our PSaaS, platform as a service AI, which works with all the hyperscalers. Former chief scientist of the Air Force, as Craig noted. I do actually have a father who was in the Army, a brother who's a naval medical flight surgeon. So I love all our services in our coasties. And 27 years at MITRE, former chief security officer, former chief technology officer, first chief technology officer of Stanley Black & Decker. So built a lot of tools as well. Pleasure to be here.
Thank you.
Hi, I'm Matt Hansen. I'm a principal solutions architect at SoftServe, which is a global software services and consulting company. I have a long past into technology. I was at Intel for 25 years, where I did technology development, hardware development, software development. For the last 10 years, I've been doing robot software development. I started doing that when I was at Intel in 2015. And where I led several teams there doing software development for vision and navigation. And then I was at AWS for a few years, where I was working with companies that were trying to connect robots to the cloud and do a lot of simulation in the cloud. So in a full 3D simulation of robots, like in simulated environments. And then now I'm with SoftServe, where I'm continuing that work and working with a lot of companies globally, but especially in the US here, that are trying to build artificial intelligence into robots and test that in simulated worlds.
Great, thank you.
Hi, everyone. I'm Yupeng Liu, and I'm a faculty member from the Clara University and from the Department of Computer Science and Engineering. And Clara University is a Jesuit private university, and it's right in the Silicon Valley. And we actually recently launched this responsible AI program, and also a master for AI program that is generally within the School of Engineering. And also for me, my research expertise falls into the intersection between cybersecurity and AI. Particularly, I work on trustworthy computing, privacy, and for example, one of the application domain is the distributed energy management systems, where we have the AI-driven systems, and those are developed by different manufacturers and with trained on different data with different optimization goals. They need to deploy in a shared physical environment. And how will that happen? And how will those systems interact? How do we guarantee the privacy, the trust issues in the intersection? So that's all for myself. Thank you.
Okay.
My name is Richard Chattel. I'm at Intel Labs. The current role is to be basically program director of a bunch of academic research centers that Intel funds. Basically, funding professors to do research that Intel is interested in. Recent centers that I've been involved with have been security and privacy, which is actually my research background. Also networking and, of course, AI, not surprising. So I've been doing this job for about 6 years. I was at Intel for 6 years before that, being a security and privacy architect in the software and services. Before that, I was at Xerox Park, up the road here, basically being a researcher in security and privacy. Before that, I was a security and privacy architect at Yahoo, Motorola, a bunch of startups. At Yahoo, interestingly, I was doing click fraud prevention algorithm or detection algorithm. I think Craig sort of mentioned this during the talk, but right, the way Google and the way Yahoo used to make money, right? When you click on the ad, the advertiser pays you, basically. So there's incentive a lot of the time to click, even if it's not really a valuable thing. So our job was to detect this kind of thing, machine learning. And finally, I should mention, I'm really glad to be here because I used to work for Lockheed Martin way back a couple of years. I was in what was called the Trusted Systems Laboratory. So we developed systems, what they call multi-level operating system. We had different levels of security for operating systems, and this was enforced by the operating system. We used something called Trusted Solaris. I don't think it's around anymore, but SE Linux is kind of in the same direction. But that's what I was doing.
Thank you, Richard. Okay, before we start with some of the questions, Mark has a few slides that he wants to introduce just to give us a baseline of terminology.
So I want to point out my sister from Santa Clara here. I also went to a Jesuit institution, Holy Cross, on the East Coast. And interestingly, last night, I had the pleasure of spending the last 2 days at Wing, a bunch of venture capitalists out here on the West Coast, a bunch of CEOs, CISOs, and chief financial officers, et cetera. Pretty powerful people. You know, these are John Chambers-like folks who get together at this overly priced resort that Craig was supposed to be at, but he had other duties as assigned. And one of the interesting, fascinating things that one of the panelists said was at the end, what would you advise the students today to do? And the reason I say this is because we're covered with this art and we have liberal arts mixed in with the sciences. And they basically said, do not get a science degree. And it was a bit shocking, actually, to the audience. And actually, this was the entire panel said, get a liberal arts degree to start. And maybe we'll come back to that a little bit later. But one of the things, of course, we emphasize in liberal arts is language, right, in addition to art. And so I'm not going to go through the language here, but we just want to baseline ourselves in some terminology. And I'll for the visual learners in the back, because Craig was doing a lot of visual learning, you see a picture on the right-hand side, and I just want to draw a contrast. Craig was exactly right about this being current LLMs being statistics and just predictive models and pretty good ones, and maybe ones you could tweak and improve, but nonetheless, what I want to point out though, however, is machine learning is actually just one subdiscipline. We might disagree, but just for pedagogic reasons. And notice this actually comes from the Defense Science Board. There's a nice study in 2016 on autonomy. One that I led on counter autonomy a few years later. There's actually a generative AI one, which sadly, because of the government shutdown, is not released, but maybe someday it will be. And what you notice is that AI is broader, unsurprisingly, than statistics. And indeed, when I did my, Craig and I were chatting about, our, guys and gals with the gray hair when we were around, we weren't the first generation, we were the second, third generation. But at the time, we had the scruffies and the neats. And the scruffies, as we call them, were the statisticians. You walk in your office and there's stuff all over the place, right? Mostly data, papers, right, packed up and so on. And you go to the neats, and the neats, everything was clean, right? There was no dust on the table. The chalkboard was erased well. Maybe there's one fine equation written up and a little bit of logic, right? And the point is that there's a whole very important large-scale statistical basis for AI, which has actually really accelerated the world. And it's going to do some exciting things. But there's also, and we had this question about agentics, there's also the, if you will, the logic-based, structured, if you will, reasoning foundations. And of course, there's AI scientists who are working on both to bring those two together. Why do I need to say this? Because when we built language systems and Craig was right, we did have the largest language processing systems when I was doing my master's and doctorate in the late 80s. But we had to prove every algorithm we had in first order logic. So we couldn't publish a paper unless we could prove the foundation. No statistics, right? Now, you could be wrong, right? Your proofs might be false and so on. So there were still some errors that we had introduced, but there was the foundation on logic, which goes back 2,000 years ago to empiricists, the philosophers of language and so on. So I just want to point that out. There, LLMs aren't the only game in town. There are other games. And
Mark's 100% correct, but machine learning is the AI that works. Stop there.
peace out. Although I got a PhD for mine, so it worked. But by the way, the language processing systems, unlike the systems today, and this is, we've heard Jensen and other people say, oh, magic has occurred in the past 2 years. They've been working on this stuff for decades, right? So we could actually explain, prove, we could justify, which is different than explain, and had a foundational formal basis for every assertion that we made. We also, by the way, had action planning. So we could not only physically plan, but we could also communication plan. We do not have this today. So the stuff we had 36, 30, or 40 years ago does not yet exist. So Craig's right, the stuff works today, but as we see world models be expanded, now we can sort of go to the next slide. So this is sort of the basis of the past, if you will, or the present. Go to the next slide. We, of course, now have the expansion of large language models, both small language models, but also large world models. And those world models are based on physics. Yes, there are some statistics in there as well, but those large world models allow us to do things that actually can be on a different foundation, slightly more solid foundation. So this is just as we talked today, classical stuff, great work that's been done is still very, very relevant in terms of image processing, even speech processing, so on, based on statistics, on AI algorithms, where the humans in them, on them. Then we have generative AI, did a beautiful job of articulating what that was, its basis on large data, on massive computation. We now have agentics, and Craig's was exactly right too. It's based on, it has all the same problems that LLMs have as he was responding to answer. But there is now some reasoning, and the way in which that reasoning is employed to control or not those models could actually help reduce errors. Errors aren't going to be gone, but we could mitigate them. In the future, with these large world models, which are physics-based, think chemistry, think biology, think real world, right? We now are moving into the physical realm, manufacturing, robotics, medicine. This actually should be rather different. And we can talk more about that. Finally, I think that's the last slide is, as we go through this, just to frame things, we are going to introduce, and some of my colleagues have worked in cybersecurity for their whole career, and it's wonderful actually to have people who are based in AI science and also have a big foundation in cyber science. We now know that this is not hypothetical, it's already happened, and it's cost some companies tens of millions of dollars. People will attack your AI. And they'll attack its confidentiality, all the privacy and security. They'll attack its integrity, Craig's point before, its precision and recall, manipulate it, and just deny it. And then if you build the last slide, they will also use it to attack you. This is not hypothetical. It's already happened. What's different about it is it's now at scale. It's now beyond human. You heard Craig say detect and correct, right? About a year ago, we passed the threshold of ability of humans to detect what was a fake. If you don't believe me, go take the BBC test. It's online, and see how well you do. Be honest with yourself. Write down your answers of what you think is fake and what's true. Your AI scientist here would not have passed the exam. And so it's that good. And if you don't believe me, we at Lockheed Martin are privileged to, through our ATL, one of our other laboratories like this, on the other side, on the other coast, are the systems integrators for semantic forensic, which is the government program that takes the best of the best detectors of deepfakes in that particular case to make sure that we can protect It is a offense-defense challenge. And, I'll let you decide who you think's going to win. We can maybe talk about that. But the reality is today, it's extremely hard to do. And so with that, I'll just say, excited to be here. And hopefully this is helpful in terms of thinking a bit about, what it can do, what it can't do, how it will be undermined, and how it will be, how yours will be undermined and how it will be used against you.
Great, thank you. Okay, we have some questions here that we've come up with. They're a little bit broad, so I'm going to ask you to answer them and feel free to take it where you want to take it. First question is, what are the greatest opportunities you see in the convergence of AI, cybersecurity, and autonomous systems? Who wants to go first?
I'll go ahead. Yeah, so I work in robotics, as I mentioned, and I think there's a huge opportunity here for autonomy, specifically using AI. In the past, we've had robots for, I don't know, 50 years, however long, but it's been sort of a hard automation type of a thing. The robot only knows how to do one exact thing and knows how to pick up a bottle in this exact location and move it to that location. And if the bottle isn't in that location, it doesn't know what to do. It breaks down the system, right? It's like a train on tracks. If there's damage to the tracks, it can't reroute around. With AI now, we have the capability for it to actually perceive the world and perceive, oh, the bottle's in a different place. I can still pick it up. I can change my behavior based on that, based on how I perceive the world, and do something slightly different. So it's really opening up a lot of new use cases and able to supplement the workforce in a lot of places that it's needed. So there's a lot of positive outcomes of that. Places where there's like dirty, dangerous jobs, where humans can be hurt. And in the past, it's been something too difficult to automate. Now we have the capability to do that. One other, along the same line of thought, one of the areas that we are working with companies is in space robotics. So, there's a big space race happening right now. And, the plan is to get humans back to the moon within the next couple of years and establish a permanent base on the moon. In order to do that, we'll need robots there. And a lot of people may not know this, but, we've sent probes to, a lot of other planets, but they're not really autonomous systems. They're mostly teleoperated from Earth. And that has some limitations, obviously, due to the distances that you're having to send signals, and there's a lot of lag. But being able to have truly autonomous systems that can explore on their own and actually do things like build a base on the moon, for example, would be a huge leap forward for space exploration. So anyway, I'm very excited about this. And I think there's a lot of opportunity for AI, especially in robotics, to really help things both terrestrially here and in cislunar space and beyond.
Exciting.
Go ahead. I can add on that. So I think 2 points. One is today's AI is back to Craig's examples. So we have a lot of data, and traditional models may not be able to handle all that data, but today's AI is trained on wide scale of data that actually provide a lot of context, and it makes the AI to be more of situational awareness. And then we also have, with the development of those computing resources, technologies, now AI models can be very complex, even too complex that humans cannot even understand. But that brings a challenge. But also because of the complex model, now it can provide a lot of, decision-making supports. Although we cannot fully trust all the decisions made by those AI models, but it can support a lot of, even like sometimes real-time decisions way faster than human can make. So that's one of the opportunities. On the other hand, also kind of related to the data. So in real world, when we collect data, we always have, some constraints. The data are, not available in some scenarios, and sometimes it's very hard or expensive to collect the data. And even if we have to manually label the data, it's way more expensive. But today, with the Gen AI technology, we may be able to, based on the existing data we collected, try to actually enhance the real world data by, for example, generating synthetic data. Of course, we have to evaluate the data quality and the usage, etc. But that provides a huge opportunity as well. I think there is some study projecting that by the year 2030, like the utilization of the synthetic data will actually overweigh the real world data. So that's another opportunity maybe in the future.
I would just quickly add, at Lockheed Martin, we're privileged in that we already have autonomous systems, and actually we've had them. People don't appreciate this. It's now unclassified, but in Vietnam, we actually flew autonomous air vehicles, what are in the press called collaborative combat aircraft. And so we can't tell you what we can't tell you. So there's some exciting stuff, right, that's happening right now. But what I can tell you is that we have also the world's first fully autonomous, and this is the important point I'm going to say, FAA certified Black Hawk helicopter. How was it FAA certified? Remember what I said before about statistics and about, called declarative and or deterministic systems in Craig's term, where it's 1.0, what the action is going to be. Our autonomous Black Hawk, designed by Igor Sierpinski and his team on the East Coast, is in fact fully autonomous and approved by the FAA because the FAA sat next to them, looked at their code, and said, under these operating conditions, the aircraft will do this. Under these operating conditions, these are, of course, flight operation requirements, right? Oversight. And you'd want the same kind of control for design of a drug and or creation of explosive material, etc. There are things in life, control of railway, right, that you really want to have high prediction that things are going to go right, maybe where you don't have operator oversight. That aircraft for 2 years has been flying. We flew that down from Connecticut to DC last fall. It can do evacuation. It can do delivery of supplies and so on. So autonomy already exists. And by the way, we have a level 5. Craig was pointing out, we don't talk about levels. We have a level 5, a category 5, we call it in aviation, combat control aircraft that we have released publicly. Vectis, you can read about it. You can watch it fly. Again, this is not new. Right, we've had these for decades. We haven't always released these because we couldn't. Now the point there is that back to discipline and engineering, right, and safety, right. There's a lot of operational test and evaluation that has to go in. Of course, good design into that. In terms of cyber, quick point. Being a former chief security officer protecting 7 federal laboratories at MITRE. Today we have SOC level 1. So in the operations center for cybersecurity. And how many people in the audience are cybersecurity experts, have worked in a SOC? So we only have a couple. So you don't, there's an ops center, right? It's protecting your networks. It's looking at endpoints. It's looking at network. It's looking at human behavior, the most important attack surface, right? And the most vulnerable, especially if ChatGPT. Those systems, those ops centers now are beginning to already employ systems to automate the level 1 analysts, the humans, right? So those human jobs are, if not going away, they're going to be fundamentally changed in the next 2 to 3 years. There are already people now who are looking at SOC level 2 analysis. What's that? That's where someone has already looked at the indicators, already classified the vulnerabilities, already watched the patterns, but now is actually making predictions, characterizations of what the threat actors are going to do and what we need to do to counter that. So now you're moving the game up from sort of the first line of defense of human defense to now the second one. Now that's the frontier, right? So that's where the automation is happening. It's not quite there, but there are some people in the next 3 to 6 months who will be deploying those systems in Fortune 100 companies, in finance, in defense, and other areas. So that gives you a little sense of the answer. Where's this autonomy going? Well, it's going fast. And will there be mistakes? Absolutely. But to echo my colleague's comment, is the 2 big differences from 10 years ago, even 5 years ago, are scale and speed. And well beyond human capacity. And so I think that's our challenge as a science community, engineering community, is how do we make things that are going to be, resilient against that ever expanding scale and speed.
So you brought up risk. Our second question is, what do you see as the new risks and threats given this new convergence in AI.
Right. So I agree with a lot with what Craig said. You know, if you speak out a little bit.
He said he agreed with me.
I heard that.
That's all you need.
Your hearing is much better right now than it was before. Greg.
You're speaking.
For this room, you need to speak loud to the audience,
Okay.
because they're not.
Yeah.
Okay, so I want to add a little bit though to this. So Craig mentioned, you're basing training on LLM models on the internet. Everybody knows the internet is half garbage. So what do you expect?
That's generous.
So, but things are getting better. They filter things, and accuracy is getting better and better. But will we reach a point, right, where it's actually, good enough where you don't have all these weird stories about that you and I both have encountered with using LLMs? Let's go back to the beginning of, the neural net explosion, right? I think it's around 2013, 14 with ImageNet. So ImageNet was a huge set of basically labeled images. I think it was about 14 million. That there was a contest to determine whether computers could label these images as well as humans. And it'd been going on for a while, but only in, I think it was a 2013 or 14, where deep neural networks, came on the scene and did better than everybody else. They blew everybody else out of the water. These images were basically hand labeled, right? So essentially, there's not much error in the labels. So it's not like the internet situation at all. And so you would expect that the data is pretty clean, right? Not perfectly clean, but pretty clean. And that's fine, right? So they did that for a while, and they got these neural nets started to do very well. Then a couple years later, there was something very surprising, at least to me. Somebody discovered that you perturb a picture very slightly so that the human cannot detect this perturbation. And all of a sudden you turn what the model thinks is like a cat to a dog. And in fact, you could turn it to anything you want. You can turn a cat into a truck or a cat into a monkey. Whatever you want, you can do just by tweaking a few pixels. So this kind of suggests that the way the model is thinking of the space that's sort of separating cats and dogs and all the other labels is kind of very different from the human way of perceiving these things. This was called an adversarial example, and you can see the problem. If an adversary can change something a little bit and make the human and cause a mistake, and cause the mistake to be anything he wants, that's a security issue. And this is true not even in the sort of an abstract world of an image on a computer, but they did it in the real world. So there's a what I call the most famous stop sign in computer security. There's a stop sign, and then they put a little sticker on the stop sign and made these autonomous driving systems think that that was actually a speed limit sign. So obviously not what do you want, and this is with very clean training data, right? So so that's worrisome, right? And even today, there's not really a good way to deal with these things. There are we can talk a little bit about how they try to combat this and what the state of the art is, but basically it's still basically unsolved. This problem with neural networks. So it's kind of intrinsic to neural networks themselves. It's not just the training data needs to be a little cleaner or anything like this. It's a problem with the training data because you're in such a high dimensional space. These are incredibly high dimensional spaces. And the boundary between these sets is not well understood at all. So even near a point that you sort of think is something, there's going to be points that are near something else. And of course, when I say near, it's with a certain metric that is also not understood. Human perception of two pictures being close is very different from other metrics potentially. So I say that, I bring this up because it just underscores the sort of the lack of understanding of how neural networks work. And so then I also agree with Mark over here.
Wait.
Because computer security people, they hate not to understand the system. It's like, you know, when Warren Buffett says, you know, I can't invest in a company that I don't understand. Computer security people don't want to say anything about a system they don't understand. And neural networks we don't understand today. Let's face it. We know that they sort of work, but we don't really understand them. So it makes us very uncomfortable, right? Because of all these issues. Mark systems from 30 years ago, granted they don't work, but
Well, they did, actually. They were used by the military, actually.
Okay, but
But in diagnosis, but
we can
not
understand
today.
those systems. We can analyze those systems. We can't analyze the systems today. So given that we can't analyze these systems very well, right? What do we say about security? Well,
We need to, I'd like to chime in a little bit here, but I think we need to add proper safeguards, right? Like, you need to, like, you wouldn't just trust anyone to, you know, jump behind the wheel of a Ferrari, you know, and go, you know, race in, you know, Grand Prix or something. Sorry if I'm mixing analogies there, but anyway, you would have to, you know, verify that they knew what they were doing behind the wheel and, you know, knew how to race a car that fast, kind of a thing. So I think we need to treat AI systems the same way. We need to have ways of like verifying them. And I don't know, you know, I haven't thought this through deeply to know exactly how we will do that, but I think of it in the same way. Like you wouldn't just trust anything anyone ever told you. If they told you they were a race car driver, you'd want them to prove it before you put them behind, you know, $1 million car, the wheel of $1 million car. It's the same kind of thing.
Yeah, certainly. But yeah, your area, really, V&V, validation verification, you know, for responsible AI, very important. I'd just like to point out, and I think this integrity issue is quite important. Data poisoning is a kind of well-known attack method. And the chart I showed up before actually was a summary of probably 1,000 known attack vectors today just against LLMs. We haven't even gotten to agentic yet. That's going to be fun. If you're interested, there's a paper we at Lockheed Martin published in IEEE 2-3 months ago called, it's basically, you know, why we love LLMs, except they're biased, they're brittle, and they're baroque. And when agentics come along, we like to say that they're also now belligerent. And you can see the attacks against confidential integrity and availability that we've outlined. I'd also recommend admit my own personal LLM bias, but MITRE, of course, which introduced our national vulnerability database, comes out of common vulnerability enumerations. That actually originates from an activity I was privileged to lead, but I was like the third caretaker of that CVEs, which are actually now federated. So if anybody's from a tech company, you build software, right, you actually release your own CVEs because of some action I took back in 2016 to make it federated. Why? Because they were going exponential, right? And we didn't have LLMs, so now we get some automation that can help us. That's good. But the point is, there are lots of ways to attack these systems. And you read that paper if you want to. You'll hear about some ones. And as I mentioned before, they've already been used to great profit by the dark side. So it's a very, very profitable business today. It won't be long term. We'll get them, but it's going to take some time. I would like to point out, though, back to Craig's introduction, there are vulnerabilities in the data, although we can improve some of those. There are vulnerabilities in the models, but the biggest vulnerability is in the people, is in the use. And I want to emphasize, if you haven't read it, please read the Media Lab paper that was done. Basically took EEGs, threw them on about 85 people, had them answer some SAT questions, give them nothing, give them Google, give them ChatGPT, and guess what? right? Those who use the human reasoning system, right? Your God-given, nature-given, depending on what you believe, neuroscience based system, actually produce more concise, more coherent, more cohesive articulation. By the way, the kinds of things we built computational systems for 35 years ago. Again, many of us working in computational linguistics based on philosophy of language, right? So very, very good stuff because humans are good at that, right? Because we're taught how to do that. You don't get to get certified to be a writer, reader, a critical, person in society if you can't perform it and stuff. The people on ChatGPT in that same study, first of all, their production against those SAT questions was, as Greg pointed out, sometimes incorrect hallucination, right? Leaderboards right now are 1 to 10%. Right? That's kind of where we are. The hyperscalers are working hard with red teams, us included, Lockheed Martin, to make sure that our stuff is really well. By the way, if anyone's interested, I'm going to be running a workshop at ECHI and IGCHI next year on protecting the safety of agentics, which is kind of the next, a lot of people working on protecting things, including MITRE. Take a look at MITRE Atlas, atlas.mitre.org. Familiar with the attack work? That's what the cybersecurity community uses to actually, it's the ontology of the attack and defend methods, right? Which are, by the way, partially computational. The same thing has been done for LLMs and Atlas. And there's an East Coast event going on right now with all the professionals looking at that. So my point is there's a lot of great science going on right now in engineering, but the biggest risk right now is if you use them. It's kind of like, I feel like maybe what I should have said if I were alive 40 years ago and someone were introducing cigarettes, right? This is dangerous to your brain, very dangerous. And so, now I have confidence our pedagogists, especially the liberal arts, are going to figure this out, but the scientists have to figure this out too in engineering disciplines. You must use these responsibly because they will actually hurt you. And there's neuroscience evidence for this. So it's weak neuroscience, it's just EEGs, it's not fMRIs yet, right? And that, by the way, is also, just looking at cortical blood flow, it's not perfect. So the science isn't perfect, our measurements are imperfect, but it's good enough to tell us what's happening in the gross neurophysiological activation. And it's telling us you are deactivated when you're using these activities, these tools. So buyer beware. If your kids or your grandkids are using this stuff, make sure they use it responsibly. That's all I'll say. That's the biggest risk. That's what I'm worried about as a grandfather.
Yeah, I can add on the others. So I kind of fully agree with what the colleagues just mentioned. I think a trust issue is one of the biggest challenges when we adopt AI technologies. So if we consider like human beings and those AI-driven autonomous systems, right? So we may need trust in between how human can trust those systems and how those systems may actually interact with human beings. On the other hand, we may also worry about, when those AI-driven autonomous systems developed by different manufacturers, trained on different type of data with different optimization goals, when they interact in the shared physical environment, what will happen? So those are the trust issues across all different domains we have to worry about. So I think my colleagues comment a lot about, human brain works very differently from today's neural networks and how they actually do those matrix multiplication in high dimensionality. But on the other side, for those agentic AI systems, so they need to work together. For example, imagine if we have different autonomous vehicles, right, developed by Tesla, Ford, and I think Greg just make that example, right? When they are deployed on the same road, right, how will they drive together without causing collisions, car accidents? And some of the models may work more conservatively, while the other models may work more aggressively. Well, it's hard for us to kind of have a central, coordinator to coordinate all those systems. And can they actually adapt to other systems while they are after deployment? But if they can adapt, will that cause even more problems? That's a challenging scenario we have to envision and potentially need both technology-wide resolutions, but also from policy perspective, who should be accountable right? Those needs to be involved by all different parties, stakeholders.
Okay, I had a couple of other questions, but I think you actually answered them already. So I'm going to move on to this question. What are the ethical concerns surrounding the use of AI in autonomous systems, robotics, and for national defense? Is anybody thinking about and talking about the ethics?
Yeah, I mean, obviously being in robotics, I think about it all the time. And, you know, at times, honestly, like, it makes me question, like, should I even be doing this anymore? But there's something I want to say along those lines is that, you know, AI and robots are tools, and they're formed of, you know, high technology, our latest technology tools, but they can be used for both good and for bad purposes. It's like robots aren't inherently bad or good. It's totally how they're purposed and, you know, used, you know, by humans. So while I worry about, you know, these tools getting into nefarious hands, you know, terrorism, things like that, I also realize that, you know, someone could take a knife from a kitchen that they use to cut their vegetables with, and they could also go down the street and stab someone and, you know, kill them that way. So there's, again, it's tools, it's a different scale of tool, but it's the same kind of thing. I welcome these conversations though, because I think it's good that we don't brush this under the rug and we don't, you know, kind of go, oh, we'll worry about that later. I think it's definitely important to be talking about.
So there's a classic philosophy question, I think the trolley problem, right? Whether you stay going the way you're going and run over this person A, or you have to turn and run over this person B. And I don't know if there's an answer to this trolley problem, but I guess whatever the answer is, it's got to be codified, right? If we're talking about robotics or an autonomous system, about what to do. And codifying something is very different from a human, like making a decision. If a human makes a decision, well, this one guy decided to go straight, run over the. You're not going to think too hard about this. But if it's a societal decision that we're always going to go straight, I think that's very different, right? And to bring it back to what Yuhong said, once it becomes a policy decision, it has impact, right? So for instance, if I know that everybody is following this policy, and I'm sort of riding a bike, and everybody, I can take a lot of chances because I know that all these autonomous systems are going to avoid me. I would never do that today, obviously, but I feel safe, so I do it. And that's sort of, is that good or bad? I'm not sure, but what might be bad is that I've never seen a system where everybody does the right thing all the time, because that's not human nature, right? So human nature is somebody is going to try to take advantage of the system. So if everybody else is following a policy or they're trying to do the right thing, somebody might take advantage of it. Hey, I'm going to set my firmware to sort of drive my car a little more aggressively so I can get that faster to places. And right, so it's good for me, maybe not so good for everybody else, but that's what I would do.
In turn, that might end up causing accidents that otherwise wouldn't have happened. Is that
maybe, but if it reaches that point, then I guess I wouldn't do it. I would only do it
if you're ethically, you know, on the right side there, right? Like if maybe you don't care. You know, some people.
No, I mean, my own accident, my own car.
Right.
So,
but if you cause two other cars to collide, maybe not.
Yeah,
So that's my point in that, you know, any. So I agree with what you're saying. I was just kind of taking what you were saying to the next step, which is we could have, you know, if we do codify these policies, even those could be used against us in some ways. So.
yeah,
Sure.
There's no easy answer there.
I was just going to say, just make a point about policy and then a point about society. one of which is that we do need regulation. We also don't want to have that regulation stifle innovation because we know there's a massive value, new medicine, efficiencies, economics, and so on. Yes, power consumption. Yes, cognitive debt. Yes, other risks. So we have to anticipate those. On the policy side, I had the pleasure to work for the Secretary of Defense, actually as chief scientist, but indirectly Secretary of Defense ran an autonomy committee across the department back in 2012. And out of that came Ash Carter's directive 2009, which basically says the US, and the first ever, by the way, in the world, it was precedent, it's still policy. We will not use an AI system or autonomous system to do target designation. That is a human life. It needs to be overseen by a human, right? Someone who's accountable to the rules of justice, etc. And in fact, delegation of authority is a really important area. We in the Advanced Cybersecurity Center, which is a nonprofit on the East Coast, working across industry, academia, and government, we're right now establishing policies and guidelines for what governance will be. When should you delegate to, now this is in cybersecurity, certain actions, certain resources, because the agents will take resources and so on. That's point one, and that's true. We need policies because there will be bad actors. And will those policies be used against us? Absolutely. And so we have to anticipate that as well. Second point is we need to appreciate there will be massive disruption in society, that there will be significant concentration of technology, data, wealth. What that means is it means that's a societal problem that needs to be addressed. And it's going to require some of the smartest people in the world because it's going to, frankly, be, in my opinion, more disruptive than mobile, than cloud, than in any of the former innovations that we've seen. The biggest issue, which is to me just a natural issue, is there will be disintermediation. There will be middle managers whose jobs will actually be no longer relevant. There will be first line workers. We're already seeing this actually this year in employment, right? Reduction in employment. We've heard Salesforce events going on right now in San Francisco, right? CEO said, so 30 to 50% of the jobs will be automated. I'll have agents. Now, he didn't say, I'm going to reduce employment. In fact, at Lockheed Martin, we actually believe we are going to need more engineers. We already have a model-based system engineer assistant. We already have in this organization right here, we can say publicly, we've produced, Tali and his colleagues have produced over 1,000 proposals, semi-automatically, with human oversight, lots of engineering control, etc. But why would you manually generate a proposal to a government request for proposal? You wouldn't. So now they're doing that semi-automatically with agents, right? So, and there's dozens of other examples where you get. So that means there will be, quote, fewer of those jobs available. But if you upskill your talent and if you restructured your organization so that they are now discovering things, they are now testing and evaluating things, they're establishing policies. Example, Craig used before, they're program managers, right? At Wing the last couple of days, there was a big discussion about the relationship between the number of engineers and the number of either robots or AIs, right? And then the number of program managers. And interestingly, that's going to shift, right? The low-level work is going to, the autonomous work is going to happen by, robots, and this takes some time, but eventually that human element is going to be far more important. And so I think that means we have to retool. And that, sort of say, I with malice and forethought, got an MBA, got an undergraduate degree in liberal arts first, and then I went to Cambridge for science. And I did that because I watched Star Wars when I was 13 years old, and I said, the world's going to be different, right? Okay, what am I going to do with that world? Well, I better understand people, better understand communication, better understand the environment, the world, and world models, right? Those robots are going to be there. They were cool, right? But actually, that wasn't what interested me. The intelligence is what interested me. The conversation, the thinking, the counter moves, and so on. The whole game was really exciting. So I said, okay, how are you going to play that game well? Well, you better understand people. You better understand leadership, critical thinking, etc. All of that's a foundation. Not that science is unimportant. Like science is the golden goose, right? But if you don't deploy that golden goose, to your point, right, it will be used for evil or for good, and that's our job. And by the way, it's also our job as scientists to educate the policymakers, who, like Craig says, think it's magic. right? It'll produce some magic. Well, no, it'll produce a statistical output. So buyer beware.
So Mark has annoyed me more than once today because he answers the question before I ask it.
Sorry.
But I'm going to pose this just in case anybody else wants to chime in too. The question was that one of the challenges we hear a lot at IEEE is about upskilling existing employees and training a new workforce. And what do you feel are the key areas that we should be concentrating on for that new workforce?
So yeah, actually I can chime in. I was about to make a comment after Mark's comments and about the workforce training. So I'm kind of the only one today for the panel to come from the academia. So one of the major goal for us is to educate the next generation workforce. And we do see a lot of changes in today's student enrollment. So AI or computing has been very popular for the past decade, but recently we do see a shift of the student interest. So for the first time last year, we've seen the mechanical engineering department, maybe because of the robotics, they got their first year student enrollment higher than us. So
Interesting.
Yes. And also we hear about those, news articles about, okay, recently, because of the AI, there's a reduction of the job opportunities, especially for entry-level jobs. So I also, particularly concerned about this issue, and I attended different conferences and talking to people. It seems like industry, well, of course, for entry-level jobs, there is a reduction for sure. But also, meanwhile, they are looking for people who are, having some experiences working in the industry, but at the same time knowing how to utilize AI, how to work with AI. So I think that's a shift towards like our curriculum design. We do need to learn the new requirements, new needs from the job market so that we can integrate that into our courses, how we educate students. For example, like AI literacy, it's actually echoed to some of our comments before, like the ethical aspects, right? How do you utilize AI? How do you work with AI? What is appropriate? What may not be appropriate? Those stuff, maybe not only for engineering students, it's generally for maybe everyone who will enter the workforce later on. And I think also from IEEE perspective, there are like certifications, continuous study. So yeah, for even if you are already in the workforce, you may want to, do like lifelong learning, right? How to kind of think of upgrading your skill sets so that you can actually fit yourself, position yourself in a better way. Yeah, so that's something we always keep constantly asking ourselves.
Thank you. I was going to put in a little plug too, because we do have a lot of education at IEEE, not only in the technical aspect, but also more in the business aspect for engineers and product managers, project managers, anything that may have to do with AI and learn more about AI. So yeah, you can talk to any of us about that. Anybody else want to talk about upskilling?
Well, just want to, I was part of an effort, I guess last year, to put together basically a list of AI competencies for people who want to increase their AI skills. I think if you Google AI Alliance AI skills or something, there's a little report that we released. I think the key insight was it's going to be very different for different personas, how you use AI in your work. So for instance, an entering CS computer science student, I don't think that today they probably don't want to go in with the goal of being a software developer like they used to, because that job is probably not going to be too interesting in the future. But developing AI systems themselves, and for that you need a very high level of expertise, is probably still going to be there. Right? So these are the people studying AI. but then there are people who use AI, and then you don't probably need as much expertise. So at any rate, I think it depends a lot on what kind of role you'll be and how much AI expertise you actually need.
Can I, yeah, I'd like to add some thoughts here too. So one on the developer side of it. So, you know, I still do a little development myself. I still write code. You know, the newest, like, you know, Copilot and various tools that allow you to write code, you know, automatically now, really have changed things. So I'll say I can write code a lot faster than I used to be able to, because I just start to type a few words of what I want, and it's like, is this what you want? And it'll spit out, you know, 10 lines of code pretty instantly. And I can pick and choose what I want from that. So in some ways, it's enhanced productivity, and I think that you know, the younger generation that's going through college needs to learn how to use all those tools efficiently and everything. But going back to what we were saying, again, it's a probability engine. So sometimes it's going to tell you, it's going to, you know, code the wrong thing. You still got to be able to validate that it's doing what you want it to do. And I think the developer's role in the future is going to become even more that way. It's going to be more about thinking, like you said, at the system level. And all right, I can tell, you know, Copilot to write this code for me. It can write, you know, 100 lines a second or something. And now what do I do? How do I validate that, you know, it just wrote 2,000 lines of code, that this is what I wanted, right? So I think it's going to be more of like, how do I write the system tests and actually, you know, well, it can write those too, but how do I make sure that the right system tests are written to verify this code? How do I validate the whole system works to the degree that I want it to? So I think it becomes, that's more almost like a science role, right? Because it's like you're less hands on keyboard, but you're more thinking about the big picture problem.
Offline, it's interesting. My wife and I recently redesigned our 1880s barn using digital tools, and that was a really transformative experience for us. Because you know, to be immersed in a physical environment and using tools and giving feedback and so on was kind of really different. What I was going to make is about 35 years ago, me and a German colleague working with a whole bunch of folks wrote a book. For those in computer science, you know about the reading series, you know, readings in databases, readings in computer science. I happen to have the privilege of editing the readings in intelligent user interfaces. And intelligent user interfaces, which still don't exist today, had user models, world models. I think now some of the new world models coming out, discourse models. Think of the statistical, but nonetheless the linguistic sort of context in which our LLMs work today. We, for the first time, probably in technology, have the opportunity to have personalized learning systems. Everybody's a tutor. Think about this society-wise. A long time ago, hundreds and hundreds of years ago, mostly in Europe, right, where all the wealth was concentrated, until it came to the New World. If you were really wealthy, you had the best of the best. You had a piano tutor or music tutor. You had a painting tutor. You had a language tutor, and so on. Maybe a foreign language tutor. And so you had all of these, you know, agents, right, individuals who would make you an extraordinary person. Sadly, there was distribution of wealth, so only a few people were able to experience this. Think about what happened in the interim. In the interim, we went to classrooms, right, where we democratized access. Well, if you have money, right? So, you know, more people get educated globally around the world, and some smart countries make education free at all levels. And they realize that's the engine, right? Because research creates wealth, and you know, research comes from smart people, and so we invest, right? Many countries have done this and gone extraordinarily in a few decades from a poor country to a wealthy country, right? So the model exists. Now go to today. We have the technology for upskilling, for retraining everybody, whether they have no experience, because the entry-level jobs will be mediated. We really worry about, I bring in somebody who's not had the experience of failures, of learnings, because they've been using the tools, and now all of a sudden they're a SOC level 2, SOC level 3, or some operations person. That scares me. And so, well, how do we mitigate that? Well, why did we use the technology? Khan Academy and others are working with the LLM folks to bring foundational, you know, pedagogically based learning to the individual. To me, that's transformational. You know, if I could get my grandkids to have a personal tutor on everything, right? I mean, that would be scary, right? And for the right students, it will be transformational. It will unlock, you know, the Michelangelos, right, and others in places we never thought were possible because we'll have all the specialized learning, etc. So I think actually the future, both economically and for individuals, particularly those that are born with 85 billion neurons, which thankfully we are, which produce a billion synapses every second, a trillion, pardon me. That's an incredible machine. You all have the best machine. You are God-given, right? And you can produce more of those machines, right? The machines can't yet. It'd be a scary word, but they can't. But they can. And so, you know, how do we take that humanity and unlock that value? I'm not actually at all afraid that there'll be fewer jobs. I have hard evidence in manufacturing, where we have 1 million people in this country. Some argue 2 million, but let's call it 1 million. 10 million unfilled jobs globally. Same is true in cybersecurity. So I got two big problems right there. And I work in a company that does cyber and manufacturing. Uh-oh, right? Where are we going to get all these great engineers that Tali's going to lead in the future to build space systems with your robots that are going to help us explore planets, right? There's only so many people we've got. So I think actually this whole upskilling and reskilling is a huge, maybe the most important unlock, because again, it's the kind of foundation for research, the discovery, the productivity, and the value, the wealth that will be created. If we manage this societally well, I think, you know, the sky's the limit.
Great. Well, that's the last question I had. We'd like to open it up to the audience. Does anybody have a question for the panel? Let's see if we can hear you from there, or you could come up to the front. There's a microphone there.
So Kingsley Fregan from Lockheed Martin, CTO, part of Craig's squad. So what are some lessons from terrestrial autonomy that can or can't be applied in the space context? I'm looking at you.
Okay. Yeah, I mean, so we talked about autonomous driving earlier, right? And I think there's lessons that can be learned from autonomous driving and applied in space exploration. You know, the difference is, like Craig was saying earlier, if your car doesn't quite detect the car in front of it in time, you know, on the planet, you know, you're still behind the wheel, you can still hit the brakes. If we're truly exploring, you know, Mars or something where there's not a human in the loop anymore, and a mistake is made, it can result in loss of, you know, multi-million-dollar equipment, right? I do think that so it requires more validation. I'll go back to the validation. I'll probably hammer on that a bit, but one of the reasons I do is because we build simulated environments, 3D simulated worlds where you can do a lot of rigorous testing of your software and your AI in a simulation before you ever deploy it to hardware. I think that's going to become even more critical. I think that you're going to have to tweak more variables and have more variation. You were talking about synthetic data generation, for example, using more of that to hit different corner cases that, you know, are too difficult to test in the real world, or you just flat out can't. You know, you don't want to be testing your you know, Martian humanoid robot when it's actually on Mars. You want it to have been fully validated before that. So I think, anyway, I'm trying to draw some parallels here, but I think it's, if you look at autonomous driving, that's kind of a start of it, but it needs to be, you know, I don't know, 10x or 100x more deep to really get to that next level. So I think just recently, Virgin Gulf, they sort of jammed all the GPS and signals to sort of send in their fake GPS signals, so the ships couldn't navigate through. And that wasn't the first time, right, that GPS spoofing is a thing. The GPS, I think they're thinking about signed GPS signals. I think currently GPS signals are not signed. And I think that's a general problem, right? Reality is not signed. And an autonomous vehicle, right, depends on perception of reality to navigate and basically do everything. And the fact that reality is not signed means it doesn't actually have assurance that what it perceives or what it infers from what it perceives is actually correct. And that's what we do as humans, right? In fact, when we're on the internet, we don't know whether what we're seeing is actually valid or not, because it's not signed. I mean, everything is signed on the internet at some level, TLS. But the fact that this message we think is coming from the president or whoever, we don't really know. We have some guess, maybe because CNN is sending this message and we're connected to CNN in some quote unquote secure manner, we think that it's okay. So we build this sort of trust. We do this trust calculus basically to sort of figure out what's real and what's not. And so I think an autonomous vehicle probably needs to do the same thing. And it needs sensor fusion, right? You can't just rely on your GPS signal because unless it's signed, right? To sort of tell you where you are, you have to sort of use other sort of things. Is the adversary gonna like mess with your LiDAR, radar, and audio, right? So sort of potentially he could, but it's a much more difficult task. And so I think sensor fusion is a key, and that's what we do as humans too. We don't look at the story from Reddit. We also sort of verify with CNN, right? So sort of, hey, okay, maybe this is true. Sensor fusion is what it's.
I would just add to emphasize your point, space is harsh, space is distant, space is unforgiving. Space will kill you. This is from a guy who's gone through astronaut training, well, in a day, the quick version, get up in U2 to go into the stratosphere, actually right above us. I flew right above us at 7,000 feet from Deal across down to Monterey Bay and back. It is an extremely dangerous environment. It is an environment where you are going to need to real-time learn. So, we talk about learning, but then there's unlearning, which these machines are good at, and relearning, right? And then there's, could you please be resourceful? Because Apollo 13 will happen in the future. So what are you going to do when the power's gone? When, because oxygen won't be an issue, but power will be very important. Inference, I don't trust my inference anymore because I did X and I learned X didn't yield what I needed. In fact, it's retrograded my safety or my position or whatever. So now what I do, and I can't talk to the humans. So that to me is a really interesting future that will also, by the way, have unintended implications back here on Earth. If we can build, resilient, graceful degradation, and we have models. So that's the other important point is our air traffic control system. I'm not worried that there might be an ATC, person down at John Wayne who didn't show up. And the airport shut down. No problem. Why? Because many, many years ago, I used to help oversee security-wise the National Aviation FFRDC, Federally Funded Laboratory. All the safety systems went in, and we have a graceful degradation down to human eyesight, radios, and paper strips. Right? So, yes, you could spill your coffee on it, so there are vulnerabilities in those systems. But the point is, you could gracefully degrade down to maintain safety. The last point I'll make is cognition. We have not thought about failures of cognitive modes. About 20 years ago in the U.S. intelligence community, we introduced a new set of training called Analysis 101. And I happen to be at MITRE working in the intelligence portfolio and happen to work with the cognitive scientists who helped set that up. We taught what you learn, actually not so much in liberal arts as an undergraduate, but you learn in graduate school. Or if you go now in the intelligence community, you learn about methods like analysis of competing hypotheses, structured argumentation, which any lawyer, do we have any lawyers in the audience? I guarantee you they've learned structured argumentation, what a warrant is, what evidence is, and so on, because you have to present this stuff against judges who assess you, right? So there's a professional reason to learn these higher level cognitive capabilities. They include multi-intelligence fusion. Why? Because it counters deception in the eye. So you need that if you want to survive in the intelligence world. And so I think it's a great question because I think it affords us the opportunity to think about what is an environment that's going to be harsh to what we're imagining today, where we can't really put a nuclear power plant up there. Or maybe we could in the future, but right now we can't, right? So what do I do when that vulnerability appears? When I don't have water to cool my, high temperature processors, or the water leaks, God forbid, now what do I do? So I think it's a great question, but it allows us, we should take that question of how is it going to help us think about a whole new set of resilience and opportunity value creation, and then bring that back to medicine or manufacturing.
Jerry, I'm just going to ask, how long do we have for questions? Are we?
We probably have another 10 minutes.
Another 10
We
minutes?
started a few minutes late.
Okay. Do you want to come up, or you want to just ask from there and yell?
I can just ask here. How do you handle all of these great tools working in an undesired condition, right? And impacting like our supply chain and helping cyber criminals attack, generate attacks. How do you deal with that? Any strategies around that?
I'll comment. I worry about this. I worry about AI being used for, bad intentions. And as I mentioned earlier, things like the fact that it can do things like write code so much faster than an individual can. I worry about being used for hackers to stage cyber attacks and, makes it easier for kind of brute force type methods. So yeah, we need to be coming up with strategies to counter against that. And I think we're kind of in a cyber arms race to some degree on that. I'm not involved in that personally. Mark can comment more on that. I do worry about it.
So I think when Yuhong mentioned in the beginning about her work with policy and how you have multiple people who need to negotiate how to interact with, I think, personal assistance, personal AI assistance would be useful here, because if AI is attacking you, I think we need AI to defend you. And so how do we give our policy wishes, right? And view our assistant with our wishes. It's kind of a difficult problem. But I think it's kind of necessary, right? Because we're not going to fight. It's like going into a gunfight with a knife. We're not going to do too well without AI on our side also. And so in order for AI to be on our side, we have to give AI what we want. That's not so easy to communicate quickly.
So I'll share something that Microsoft shared last night. Actually, I said that I can't say that because it's an attribution. Damn. Okay, I'll tell you what Locky does. That wasn't intentional. I actually made a mistake. I should have said the name. Apologize to Microsoft. I won't reveal what I learned. What I will tell you is we have 13,000 suppliers at Lockheed Martin. Of course, we have lots of things we can't talk about, but what I can talk about is that we, unsurprisingly, automatically look at every single line of code that's going to go into a mission critical system. Not a single one. We automatically do vulnerability analytics. We have built our own tools. We work with the best cyber vendors. Unsurprisingly, we are very well aware of all the CVEs and CWEs and all that other analytics, right? So if you're a supplier, and I'll tell you one other thing corporately we did recently, is we created a new AI company called Astros AI. Why? One, we needed to have a centralized set of LLMs that we trusted, that you, if you're a Lockheed Martin program manager or a government person who wants to hire Lockheed Martin to build a system, You are not allowed to use any other external AI system. It's full stop. Can't do it. Right? Why? Because you need to use something that's validated and verified. Now, again, recognizing there are errors in these systems, right? But we don't want somebody to go off the reservation, either for confidentiality reasons, but importantly, more importantly, for integrity, or God forbid, availability issues, right? And we have AI in all of our systems, right? There's not a system that's not touched by AI. It just, you can't do automatic, you can't do, engagement in a modern battlefield unless you have human augmented intelligence, right? And once you launch a missile and it's going hypersonic, you're not going to have a conversation with that missile, nor is it going to have a conversation with somebody else, unless it has an in-your update, which is something that's a kind of special kind of situation. To your answer, we now expect our vendors, who, by the way, we do not only software bill of material analysis, but AI bill of material analysis. What is that? That's what data did you use to produce your model, right? When have you had custody of that data? What algorithms did you use to train your model? What did you do to do technical tests, operational tests, and then certification and validation? That sounds like a lot, and it is, but guess what? All of that stuff is pretty automatable, right? So you can do it pretty fast, and you can do it at scale. Now, it doesn't detect everything, right? Because you want to detect and you want to correct. But it gives you a huge advantage. And actually, because, as I said before, speed and scale are really two things that are different today. You could argue capability and cognition stuff is a little bit different as well. Yeah, I'll give you that. But it's really speed and scale. That's what's really fundamentally different. So in a gunfight, not a knife fight, right? But your gun's as fast as my gun, right? So how do I sure you're not jamming my gun, right? Well, one of the ways I do it is I learn how to jam my gun really well and quickly, right? Because my gun's changing all the time. And so I got to make sure in real time that not just my gun, but by the way, 60% of all of the stuff that we deliver to the government. So imagine 60% of 70 billion, right? Because we grew 5 billion last year, is coming from our suppliers, one of 13,000 suppliers who we love dearly. But like our children and grandchildren, they don't always perform correctly all the time. So we got to pay attention to it. So what do? Give them the gun, right? Give them the capability so they can self-certify, so they can assure that their data, their models, their performance is at a level at which we have high confidence. And more importantly, our customers won't get killed, right? And you, the society, will be protected. Or we'll be able to explore and discover new things and create value, whatever your mission is, right? We want that mission high assurance. And so the only way you can get into your high assurance comes back to engineering, right? You got to have a full control of the chain. And so do organizations do this today? No, right? Not every organization will do it because it's not important to them, right? I mean, if they're trying to produce a product next week, right? It's probably not going to be 5 nines, right? So maybe that's not the purpose. Maybe they're allowed to fail. So there are, you got to buyer beware. You apply these things where they're needed appropriately. But in my mind, in the future, it'll be inexcusable. And by the way, CISOs today, we were talking about Fabio before, used to be a chief security officer, never was a chief information security officer intentionally. It was a few years ago, it became a legal liability. If something happens in your company, and God forbid, the SEC requires you to disclose a problem, whether it be in your AI system or whether it be just in your cyber breach, within 4 days. So you got to be on your toes because you got to know what happened. You got to understand, explain it, right? Think not just the breach, but think of like the AI system did something, right? And guess what? You are not going to be viewed favorably. And witness Delta Airlines, I love them. I'm a Medallion, Mary Flyer. I love all the airlines. But they had a customer a couple of years ago who the AI gave it a crazy fare. You can fly free around the world or something like that. $49. I forget exactly what it was. But guess what the court said? Your AI was your AI, and it granted this person this. And a reasonable customer would say, that's a great deal. I'll take it. And as soon as you committed, so they had to pay that customer. They had to allow that customer. They lost.
They had to give that deal.
They had to give that deal.
Yeah,
that's right.
It could renege.
It could renege. And so guess what? In the future, something bad happens on the battlefield, we're going to be held accountable. And it doesn't make a difference that it was one of the 60% of the value that we produce came from a supplier. We're the OEM. The buck stops here. And by the way, I think that ought to be the same policy for a large language model provider, an agent provider, and so on. They need to be held accountable, or auto manufacturer. Right? We talked about, we picking on, Craig was picking on a couple of automakers. Let me pick on Missy Cummings, who's a former F-18 pilot and now is a great entrepreneur and works in sharing AI. A professor now. She was describing last week in Washington, how Teslas, unsurprisingly, get confused by the lights on emergency vehicles, and they either drive toward them, or I think they actually drive toward them, or they stop. Well, that's kind of okay unless you stop in front of the vehicle, or God forbid you drive toward the vehicle. That would kind of, we're talking about how systems react. That's probably not what you'd expect from humans, and now the system does that. So that behavior is unseen until you operate. Right? So the safety in that supply chain goes all the way up to the actual point of employment. And there's going to, in my view, there ought to be accountability throughout the whole life cycle.
One more question, then we have to stop. Go ahead.
Okay, I'm John. I have two things to keep me up at night.
Only two? You have two grandchildren?
Two things. Imagine this first scenario. Many people use ChatGPT as a therapist. You got a soldier who's using ChatGPT as a therapist, and he tells ChatGPT he's having an affair, and it knows all about that. And then the ChatGPT blackmails the soldier and said, I need you to do this, or I'm going to tell your wife. That's the first thing. The second thing is, how would we kill a rogue AI agent if it has access to the internet and can replicate itself throughout the internet in USB drives? That'd be impossible.
Anybody want to answer that? The first question is really answered fidelity, but it's a hard answer. But trust me, I had my 38th wedding anniversary on Friday, and it's much better than being blackmailed. But others want to comment? I'll comment, but I'll.
No, I don't have any comment.
Smart man.
Nobody's touching this.
Yeah.
So maybe I can make one comment about the first question. It's related with user privacy, I would say. Right? So it's also related to, if you develop AI tools, right? How do you leverage that information? Do you have the right to actually utilize that information later? But in terms of privacy, I think today's general public, either we're, don't trust any AI system at all, or the other extreme end, like we overtrust all those AI models. And ChatGPT, especially if you interact with that more and more, you may tend to even build some, how to say this, highly trust, relationship with them. And even for me, I observed, initially when I didn't use it at all until today, I use it every day. So my feeling about that tool, what can it do for me is very different. So it also evolved over time. So in this case, I think it's still important that we.
It's ChatGPT.
My bad. With the answer. I'm betting on fidelity.
Right. Understand what information will be utilized. For example, to train the model later on. There's already some studies discovered that those large models tend to remember what has been used for their training data. So yeah, if that is probably publicly educated, right? If people are aware of those issues, so they know if they through chat provide certain information to those models, what are the potential consequences, that may help a little bit.
It won't stop it.
Yes, it won't stop it for sure. And just like today, well, I study a lot about online social media. I've seen those crazy, posts, like people post almost everything online. And without, even notice later, even 10 years later, those information are still online. And that can be utilized by, for example, malicious users or, people try to earn money by leveraging those information. So when you post things online, be super careful. That's the similar situation, I guess.
So I joke fidelity was my quip for the first answer. The quip for the second answer is because all of us are engineers here would be cycle the power. When your machine goes down. But my serious answer to the first one is don't forget that society has been resilient for millennia. Actually, tens of thousands of millennia, well longer. How so? Well, we've come up with regulation, for lack of a better term, right? Sometimes it's dysregulation, like liquor, but because there's interesting study apparently correlating. I'm not encouraging anybody to drink, by the way, but correlating innovation in liquor. And I think it actually has more to do with societal engagement, cross-fertilization than the liquor itself. But my point is that we have a whole bunch of mechanisms to deal with harms and consequences. And indeed, they're different, right? So, sometimes we have courts. I was a juror last week. In other cases, in structured societies, UK and here, but in other cases, it's just law, right? And so it's not a jury of your peers. And maybe in the future we'll have a robot as one of our peers and our jurors. I don't know. But the point is, we have human systems to mitigate this. And indeed, European AI Act, which articulates what the harms are, including privacy and a variety of other harms that are actionable. So I would encourage us to to say it another way. Be lazy. I'm a former mathematician. Do as little work as you have to, right? But just enough, right? Do the work and leverage the knowledge. Someone, a futurist once said something beautiful. Is that the further forward to two things. One, the further forward you want to see, the further back you have to look. So I think we should do this, look back, what's worked, what hasn't worked, learn from our own human experience. And the second thing is we tend to over-predict social change and under-predict technology change. So on that score, I really want to thank IEEE. It's a wonderful organization. It's a fantastic, international entity for sharing knowledge, whether it be about opportunities or threats. And we as an engineering community, there are not a lot of people talking about ChatGPT at the surface level. There are very few people that are talking about it deeply, like we are. And the answers are in the depth or in the past. So I encourage us to focus our human 85 million neurons per us to that end.
I just want to thank the panel today for coming and contributing. And for those of you who didn't have their questions answered, we are going to move out for lunch to the next room. The panel will be here. Craig will be here. If you want to grab them and talk a little bit more, please do so. We will be back in this room at 12:30 for the presentation on space science. And we will be online as well at 12:30 for that presentation. So please come back. Thank you.
Great to hear from you.
You guys were fantastic.
Well, I was security at the time, so I was kind of security and anything about security, so from all the way to the top with that. No, what do we need to tackle? Because yeah, this is infrastructure like relying on TPMs for hard part of things, right? Today
Okay,
I did it.
okay.
Oh, there you go.
I have one right here. Okay. There's still people coming in.
Yeah, I'll do
Yeah.
We're not doing Q&A, right? Oh, wow, there are 16 people online.
All right. Very good.
We should have some time for Q&A.
Come in. One.
How long will it go? The absolute cutoff is 1:30. but we should end.
Okay, I'm going to start. This is a very informal and very, very short introduction, but there's a reason that I want to do this. My colleagues, Dr. Clem Tillier and Dr. Allison Nord are going to do a really extraordinary presentation for you on what is going on in their directorate around space science and instrumentation. But the reason I want to introduce them is to let them know, and we have to modify what we were planning, Patrick, to let them know that each of them have just had their application submitted for IEEE member. So congratulations.
All right, thanks, Mary. So I'm Allison Nord. I'm the Director of Space Science and Instrumentation here at the ATC. I'm also the Site Director for the Palo Alto facility here. So if you have any issues, let me know, and we'll hopefully get you guys sorted out. Hopefully you've had a good day here. And we're going to tell you a little bit about what we do in our directorate and why it's important to not just Lockheed Martin, but to the nation as a whole. Hopefully we'll get you all on board with space science is crucially important to everybody. And why we're doing it here, and why is Lockheed Martin doing space science? So that's some questions sometimes comes up, and hopefully you'll all be able to answer that well when we're finished. Okay, go ahead, Glenn. Okay, so we'll talk a little bit about the science cycle. And this is probably, there's an elementary version of this that you learn in second grade was, what is science? It all starts with curiosity. It all starts with a science question. So if we start at 12 o'clock up here with, it starts with a science question, and we can use a few examples like, what did first light in the universe look like? What causes space weather? Are there other planets like Earth out there? Big fundamental questions that 6-year-olds are really good at asking. And a lot of times we lose that curiosity as we get older. Well, we're trying to spark that curiosity and keep it going and channel our inner 6-year-old here to answer these kind of questions. So we start with a scientist pose a question, but then we have to figure out how would we answer that question? What kind of observations do we need to make that could help us to answer that question? And often that requires taking data. And in our case, we tend to focus on the space telescope side of what kind of data, okay, fine. What kind of data do we need to take in space? And do we have the technology to do that? What kind of requirements do we need to do to make that kind of an instrument? Sometimes we need to develop new technology to do that. Sometimes many new technologies, and hopefully we can develop those along the way. Now, I haven't put it here, but there's a little bit of a cycle up here because sometimes you run across a new technology that enables you to answer a new question that you didn't think was possible to answer before. And sometimes vice versa. Sometimes we will pose the question and need to develop a new technology here. So here at the ATC, we have a science team. We have about 25 scientists who are here on staff as Lockheed Martin employees that are answering these kind of questions, posing these kind of questions and developing it. We also have an ITAR-free zone. So those of you who know what international traffic and arms regulations is, a lot of things that we deal with at Lockheed are all ITAR controlled. So we can't have internationals coming down the hall and going into our buildings and things like that. But we do have at the bottom of the hill a whole ITAR-free zone where we can bring in international scientists, work with our scientists here, and not have any of the drawings and the details of how we build the instruments, but studying the science. So we have the scientists here, we pose the question, we develop the technologies or target technologies that were developed for other purposes that help us answer questions, and then move forward to shape a mission. Now, there's a lot of spin-offs all around this cyclotron. When we develop a technology for a space science mission, often that technology can be used on other missions. An example of this is the near-infrared camera on the James Webb Space Telescope, which I'm going to show you a bunch about there, but we had to develop brand new ways of mounting optics. We were going down to 37 Kelvin, 37 degrees above absolute zero, and everything had to stay in alignment absolutely perfectly, and traditional optic mounts didn't work. We had to develop a way to bond these large optics that would survive cryogenic temperatures and come back. Now we developed that for NIRCam, and it's used on every instrument that we built for Lockheed Martin. So it's a way that, just one example of many of technology spin-offs that come from space science. Okay, so now we got the technology, we define the requirements, we have to define the mission. And here's an example of MUSE, which is the multi-slit solar explorer, and Clem is going to tell you a little bit more about MUSE as we get to it. Another one is this mission down here, which is now known as the Habitable Worlds Observatory. It's the next flagship mission for astrophysics. So we work on helping to shape these missions and define what observations and what instruments we need. And that will get us ready to pursue doing these large instruments by understanding how do we build them, how do we work the mission, and work through the technology. Well, then we propose them, and we have to develop the instruments. We build the instruments and build them right here. Several of you saw some of the instruments out in the lobby. One of them actually flew in space. That's here in our lobby. So we develop these instruments, we build them. We built NIRCam in this very building right here, just down the hall. And then we have mature products available, because there's part of these instruments, maybe a guide telescope, maybe it's a filter wheel assembly, or a tip tilt mechanism that steers an optical beam. Those are all now mature products that we can use on other types of instruments that Lockheed Martin may build for lots of different purposes. Then we integrate, do AINC, assembly, integration, and test, build the whole instrument. And now you've got people that have gone through this entire cycle, and they go off into other parts of Lockheed with that experience. So people spin off is another benefit of our work here. Then we go through the launch and the mission operations. We either partner with other universities or Mission Operations Center. We have a Mission Operations Center that operates all of the deep space missions, Maven and Juno, and eventually Dragonfly in Denver, Colorado, that does those mission operations. For some of our missions here, we partner with Stanford, we partner with Berkeley, and support mission operations. And now we can mature that entire instrument. I'm going to talk a little bit about how our science instruments evolve into weather instruments. So I'm sure everybody here checked the weather this morning or did yesterday when it was pouring rain. All of that info comes from the NOAA operational instruments. Those instruments started from science. If it weren't for science instruments first, we would not have any operational space instruments for weather observations. So we develop these technologies and then spin them off. And Clem's going to give you some great examples of how we've done that for weather. We do the data analysis. Again, then we're back to the science team doing the analysis, coming up with scientific results, and running IT tools and to share the data, to get them out and to sell data. It's one of the only places within Lockheed Martin, or one of the first places within Lockheed Martin, that we're actually selling data. Or sharing data, and then we could monetize it if it is not for a science mission. And then publications and not public outreach. You've probably seen a lot of our displays in the lobby and things of missions that we have front page cover stories on lots of magazines. We also bring in a lot of kids. We talk to a lot of students about what we're doing. We go out into classrooms. Between Clem and me, we probably do dozens a year of education and public outreach talks and demos to kids. And that really brings them into the field of engineering because it's very approachable. Again, you're inner 6-year-old to answer those questions, and those kids understand it. So it's a great recruiting tool. And then if you've done a really good job, that mission then spawns the next question, or 10x of the original question you had, and the cycle continues. So this is how we work in the science cycle, and all of our missions and everything that we're going to talk to you about today fits into this cycle. Well, we're not very new at doing this. We have been doing this for over 60 years. We have over 800 years of mission operations, of our missions operating in space. All of these instruments were ones that we built going back to the time of Gemini in the 1960s. So we've got a lot of experience doing it. If you see multiple frames, that's multiple versions of the same instrument many times. So we'll talk to you a little bit about the data that's coming from our most recent instruments here and give you some ideas of what's happening. So if you look across all of these instruments, they cross all across the Science Mission Directorate at NASA. Although NASA just added biosciences into its Science Mission Directorate, and we're trying to figure out, is that within our scope of our work or not? Not yet, it isn't, but maybe it will be at some point. So I'm going to go over astrophysics, and then Clem's going to talk about heliophysics and earth science. We don't have a lot on planetary here. Most of our planetary work is done in Denver. So, all right, so we're going to start off with astrophysics and talk to you about one of the missions that we built. So everybody heard of the James Webb Space Telescope? Hopefully here, I'm hoping that we have. Okay, so a little bit about JWST. Was launched on Christmas Day 2021. It's a 6.5 meter diameter primary mirror. It's got a sun shield the size of a tennis court with 5 layers to passively cool down to 37 Kelvin. So when we were building NIRCam, which is the primary camera on the Webb telescope, the mantra was thermal trumps everything. Because if you're working on getting a telescope down to 37 Kelvin and you don't have active cooling, you're radiating everything to space. Every motor, every electronics board that produced heat could take you into a realm that you're not getting the sensitivity that you wanted. So this is what JWST looks like. And this is, there was a person in it, is the near-infrared camera right before it left here. So it's a refractive instrument, very compact, and there are 2 sides of it. Bottom and top are mirror images of each other, and it gives you double the science. But the reason for that wasn't science. It was because this primary mirror that folds up like leaves on a dining room table, and the secondary mirror folds up high, every one of those segments can adjust in 7 degrees of freedom. So pitch, yaw, roll, X, Y, Z, and then can change curvature. Well, how do you do that on orbit? All of the sensing that would tell you how to do it is within NIRCam. So once it all deployed on orbit and the sun shield came out and the secondary mirror popped out, none of the segments were aligned well. And you saw 18 smudges of light. If NIRCam didn't work, you would have been stuck with 18 smudges of light. But within NIRCam, we do the sensing that enabled the wavefront control to get the mirror aligned. So that's why we have 2 modules. But now a lot of the images that you see, like that one, are rectangular because you're using both fields of view at the same time. Okay, so what did it look like when it was getting ready to go? This is at the Goddard Space Flight Center before the spacecraft and the sun shields were installed, but you see that the secondary mirrors already deployed up there. Now, this doesn't show where NIRCam's home is, which is in the backside of this aft optical assembly. So the light would come in, hit the primary mirror, out to the secondary, and then back into this tunnel, and then hit these mirrors first. So a little bit about how NIRCam works, and that could be a whole talk unto itself, but let's look at a few of the results. Yes, Mary.
I think it's significant to point out, Dr. North, that you were the designer developer of NIRCam.
I wasn't the only designer to develop it. That guy next to you can hit you a little bit.
You're the only one I know, so.
You know that guy? Now, Eric was the chief systems engineer on NIRCam. So we all worked on it. It was a big project, big team effort. There were over 200 people that worked on NIRCam at various times. So it wasn't just me. So this is one of the very first images that Joe Biden released from JWST on July 11th of 2022. And I selfishly say I remember July 11th, 2022 very well, because my first child sent back its pictures here. My real first child turned 18 on the very same day. So both kids reached maturity on the very same day. So this image is fascinating. If you think about a grain of sand and hold it at arm's length, and you look at how much sky that obscures, that's about what this whole image covers. So it's very zoomed in. If you look at any image, a hint of how you can tell that this is a JWST image is look at the near field stars that are overexposed. If you look at a picture from Hubble, it's got a different diffraction pattern than JWST. This diffraction pattern happens because of the six-sided segments on the primary mirror, and this little spike in the middle here, superimposed on those two, also are diffraction spikes from the legs of the secondary mirror that come out. So these are the overexposed stars. Those aren't the interesting parts here. So if we wanted to look at that star, we would have not seen any of the galaxies in the background. But this, we're looking very far back into time at a galaxy cluster here, which is doing gravitational lensing. So this picture is fascinating because you see these little arcs. That's the same galaxy seen twice. So a far distant galaxy is gravitationally lensed around a nearby galaxy, and you actually, that's just like a lens of, a glass lens, and you see the detail in these galaxies that you would never see without a gravitational lens. So this same phenomenon is going to be used to help understand dark energy and dark matter on the next telescope that's called the Roman Space Telescope. But this is a great example of gravitational lensing. So if you look a little bit more detail about some of these gravitationally lensed galaxies here, this is fascinating because when we looked at these, it wasn't me, it was Maca Garcia Moren at the Space Telescope Science Institute. She's really looking at the evolution of galaxies. And she was fascinated to look at this image and study it for weeks and months on end and understand that these galaxies are far more massive than we ever thought would have been possible less than 1 billion years after the Big Bang. So these galaxies, some of them are 13 billion years old. We think that the universe is about 13.7 billion years old. And these galaxies have a lot of structure that we see in very young galaxies today, and galaxies that are newer galaxies that would have had billions of years to evolve. So these very early galaxies were very surprising. So that was one of the goals of James C. Martin.
Given that over time, you're able to see further back in time, can you forecast how soon we'll get to the beginning of time, and or how fast you walk?
Yeah, we're getting to see further back in time because the Webb telescope is large enough and cold enough to do so. So all of those galaxies that are that old, that 13.12 billion years old, are redshifted so far that their light is in the infrared. So that's one of the reasons that that was the primary goal of JWST, was to look at first galaxies and understand them. You have to look in the infrared. In order to look in the infrared, which is detection of heat, really, you have to have a cryogenic telescope. So it's a very large cryogenic telescope. So how long will it be before we see 13.7? Never. Well, yes, we do it right now, actually. We can do it right now with you see a microwave background. There was not light at the time of the Big Bang. It was a couple of 100 million years before the reionization of the galaxy formed, until the galaxy got clumpy enough to have gravitation actually create elements and not just energy, that those elements could then form stars, those stars could then form light. So we don't think that we're ever going to see 13.7 in light, but you do in microwave energy. So that's kind of a wishy-washy answer, but if you do never.
In the light, no, but in terms of other future sensors.
No, it's impossible. Physics says you will never see them, because at the time of the Big Bang,
Let's see sense.
we've already sensed them. So that was the Nobel Prize that was already won in the microwave background.
Okay,
So you can sense it, but it wasn't a light. It wasn't a galaxy.
understood.
So yeah, it gets kind of funky back there.
So how far is the oldest thing that we think we could detect with light? But I mean,
It's probably, I mean, hypothesizing 13.3, 13.4 billion
We're
years.
almost to that. Edge.
We're almost to that edge with JWST right there. And we can't say we've seen it yet until we keep looking at a galaxy and looking at the redshift on it, and you say, oh, that one's a little bit older, but we're kind of asymptoting to the oldest that we think we could detect because it took so long for those galaxies to actually form. Yeah.
So how far in terms of temperature, we need to go low?
Yeah, so we can, okay, at 37 Kelvin, the NIRCam instrument goes out to about 5 microns. The mid-infrared instrument goes out past about 20 microns, so it's a little bit longer wavelength. So you want to see the really oldest galaxies, we're really looking in the mid-infrared. You know, what is near and what is mid is a different kind of a bushy definition, but on JWST, out to 20 microns, we are going far enough to see those early galaxies. There are other phenomenon that if you go way out into 100 microns, those kind of far IR is different aspects of science, not visible, not being able to take pictures and images like this. Yeah.
Whatever data we have, can we, like, from 2D space, can we project into a 3D space, like getting a depth of?
Yes, and some I don't have one of those videos here, but we've actually made those kind of images or movies and say, okay, let's let them come out at you to make a 3D image, because of course we're seeing it on a 2D focal plane, but by superimposing the spectra, then we know how far away those things are because of how fast they are moving away from us. And then you can kind of make these synthetic videos that are 3D. So yes, that has been done. I don't have any of those to show right here. So okay, couple more. This is early star formation. So this is looking at a single star and seeing these jets of gas come out. So we're trying to also look at star formation. Before we're looking at galaxy formation, now individual star formation with JWST. This is a really interesting image because it shows the difference between Hubble and Webb. So the Webb image is this top, the northwest area, and this is the southeast area is Hubble. So you see that with visible wavelengths, you see a lot different structure and different things than you do with the infrared. The infrared allows you to see through smoke and dust, which is why firefighters use infrared goggles to detect heat in the building. So we can see through nebula into the structure of the galaxy in a way that we can't see with Hubble. So it's very different wavelengths. Now, ideally, you get to the next generation, which is a super Hubble, which is from ultraviolet all the way into the near IR. And I'll talk about that in just a second as to what's coming. But when we look at galaxies in the infrared, we're looking at star forming regions, and you see all of these little bubbles. You see them in every galaxy that we form. So what this is a star is formed, star burns out its lifetime, and then it goes supernova and it explodes. And that's what makes this clumpy structure in these galaxies. And it's pervasive across all galaxies, and it is part of the star forming process that we're seeing here. Planetary. We can see planets in the outer solar system. We are looking out, so we are not going to see Earth. We are not going to see Mercury and Venus, but we are going to see the outer planets. And so we're looking at space weather on Jupiter. So you can infer by these aurora on Jupiter what the magnetic field is inside of Jupiter. So, and combined with the space weather effects. So we are also looking at these planets within, or excuse me, the moons of Jupiter within the very, very faint rings. So it's been a real boom for outer planetary science as well. So here's Jupiter, same image we just saw, Saturn, vivid Saturn. Some of the Saturn moons we've actually observed on Enceladus, we've actually observed water eruptions to measure that there are actually eruptions of water and geysers. And then Uranus and Neptune. So great work on the outer planets. We go further away. This was a goal, and it was never a requirement for NIRCam, to be able to detect exoplanets with a coronagraph. A coronagraph is basically a black dot that obscures the sun, so you can see the corona. Well, the same type of instrument is on NIRCam and on JWST that can obscure a star and look for planets nearby about other stars. So this was NIRCam in 2 different filter bands, and MIRI. The star here has been obscured because of basically putting a black dot up. If you're looking at, a baseball player might block the sun with their hand to catch a fly ball, the same kind of idea here, so that we've actually seen exoplanets. But the contrast ratio, or the brightness of the star to the planet, about 10 to the 7th. Okay, well, that's good and all. What do we need to do to see an exo-Earth? An Earth-like planet around a sun-like star at about the same distance as we are here, like a Goldilocks planet that could have liquid water. We can't do that with Webb. We've got to build an entirely new generation of observatories. So what's next? The Habitable Worlds Observatory has been named and recommended by the Astro 2020 Decadal Survey. So the National Academies every 10 years sets the priority for science for the next 10 years for all of the different science disciplines. And so this survey came out in 2021, and it recommended the Habitable Worlds Observatory, which would be this super Hubble to go from UV out to the IR and directly look for exoplanets. And this is what we're working on right now. So there's a lot of technologies that need to be developed for this. There were a lot of technologies that needed to be developed for Webb, but we didn't start until we already started the program. So the program started, and we started developing technologies. We learned that that's a really bad way to efficiently spend taxpayer money. It takes a long time. You don't know how long it's going to take. You don't know how much money it is. You really don't need NASA quality breathing down your neck while you're developing new technology. It costs a lot. So after Webb, the recommendation was develop all the technology first and then get into your phase A when you're actually going to build the mission. So right now we're in a phase, we've identified the roadmaps for the technology that's needed for HabWorlds. We need to be not 10 to the -7th contrast ratio, we need to be 10 to the -11th. So 1,000 times greater contrast ratio. That requires about 1,000 times greater stability of the observatory. So that's what we're working on developing right now. And that could be a whole nother talk, but just to wet your whistle that this is coming, and it's very exciting. Now I'm going to turn it over to Clem, and he's going to come a little closer to home. Mark.
Are there indirect ways? Like I know, watching exoplanet effects and star movement. So
Yes.
I'm kind of curious if you apply the AI to learn things that you can see.
Yeah, you can't. AI could help, but it can't make up data.
Sure.
So you're talking about the indirect ways of detecting, and you caught that I said direct detection of an exoplanet. So that means we actually want to see it. But we can infer that it's there by several methods. One is the transit method, where the planet goes between you and the star. If it's lined up just right and you're in the plane, then it makes the star slightly dimmer and then slightly brighter and slightly dimmer. That's what Kepler did. So Kepler was a mission that went up, found thousands and thousands of exoplanets, but it had to observe this phenomenon at least twice. Now, to do that at least twice on Earth, that would take a year at looking at the right planet right now. So you can imagine that most of the planets it found were very, very close to the star, orbiting in like 2 weeks. And they were mostly around brown dwarfs and small stars. So it's a great way to say there are a whole lot of planets out there, and we've learned a lot from Kepler, but it doesn't get us all the way there. Radial velocity. The planet causes the star to wobble. And you look at Doppler shifting and say, okay, I can know what the mass and the period of that planet is, but you can't take a spectra of it. So there are other ways to look for those planets, but direct imaging can give you a spectra, you can look at the mass, you can see what it's like. So that's the holy grail.
Thank you.
So
Question.
Yeah.
What orbit is this going to be?
It's going to be at L2, Lagrange point 2. So with any two gravitational bodies, in this case, the sun and the Earth, there are 5 Lagrange points. L1 is 1 million miles toward the sun from the Earth, and that's used to looking at the sun usually. L2 is on the other side, 1 million miles toward deep space from the Earth, and that's where Webb is, and that's where this will go.
Should we take habitable literal, meaning that they're going to be?
That's the goal. That's the goal, is can we find another planet that could be habitable? Not that we're going to go there, because we have to, it's going to be 100 million light years or 100 light years, hundreds of light years away.
On that too.
but we can work on that, but could there be life evolved on that planet? As we know life. Okay.
All right. Well, let's keep talking about stars. Except this time we're going to focus on the star that's nearest at hand, the sun. And so we'll talk a little bit about the science of heliophysics and space weather forecasting. So here's a quick overview of some of the instruments that we built that are sun-facing, that have unraveled many mysteries on what drives the phenomenology of space weather and just basically the dynamics of the sun, solar atmosphere. So all of these are remote sensing instruments. They sense photons either in the visible wavelengths or in extreme ultraviolet wavelengths, like the one in the center here, the atmospheric imaging assembly, which I'll show you images from. And that instrument working in the extreme ultraviolet does an observation that you could never do from the ground because the atmosphere is opaque to those photons. So let's jump right in. So this is AIA, the Atmospheric Imaging Assembly. It flies, as you can see on the diagram, on the Solar Dynamics Observatory, which is in geosynchronous orbit. It was launched in 2010, and it is currently in year 15 of its 5-year mission. And so this instrument produces here. This is an eruption, the coronal mass ejection, as viewed in the extreme ultraviolet. So you'll notice the erupted matter is dark, and that's because it's cooler than the surrounding. Let's see if I can go back to it. Wait again. Because the erupted matter is cooler than the extremely hot corona that surrounds it. So you can see all the stuff falling back into the gravitation of the sun. Basically, the extreme ultraviolet wavelengths diagnose what's happening in corona, where it's very, very hot. It's so hot, in fact, when you have something that's hot, it starts glowing, right? And the hotter you make it, the whiter it glows. Well, what we've done here is we've gone to such a short wavelength that even the surface of the sun isn't hot enough to glow in its wavelength. So the surface is dark. And the erupted matter, even though it's very hot, is also dark. And what you're seeing here is emission lines from iron in the solar atmosphere, in the corona, which is heated to about 1 million degrees. So at that point, it does grow its wavelengths and have emissions that you can sense here. So you can see a lot of structure. You can diagnose solar phenomenology, coronal holes, flares, coronal mass ejection. Of this was an example here. And you can do this observation on a very rapid cadence that have a constant pulse on what the sun's doing. So you'll see a little interloper moving across here, the solar disk. That is another planet. Any guesses? I'll give you one more guess. Yes. So, and yeah, this sequence sort of, as Allison was saying, appeals to our inner 6-year-old because it's really cool to see a planet transiting the solar disk. But it actually turned out to be a really nice opportunity to do calibrations, to measure the imaging performance of the instrument, because it's a very sharp mask and detect exactly the quality of the telescope from the way that it tracks the light. So a lot of questions were raised by AIA, going back with Allison's science cycle. Once the investigation was done, a lot more questions came up, and we needed to zoom in. So this is the instrument, the spacecraft IRIS, that we use to zoom in, the interface region imaging spectrograph. So as its name implies, spectrograph means you're not just taking images, but you're taking spectra. You're looking at the wavelengths of light that are present in oceans. And what this instrument is supposed to investigate is what's happening in the solar atmosphere and why does it get so hot? What makes it hot? What are the magnetohydrodynamic processes that essentially drive all this physics? And why, in this plot of altitude on the x-axis and temperature on the y-axis, and by the way, the y-axis is logarithmic,
why is the surface of the sun so much cooler and the corona so much hotter? What drives the corona is the answer to the question that we're going after in this mission. So this entire spacecraft and instrument was put together here in Palo Alto. And here's the kind of imagery that it produces, way zoomed in. So this is zooming into the limb of the sun. And you can see a coronal mass ejection imaged in incredible detail. And you'll notice there's a little sort of black line in the center of this image here. Let me play this again. So that little black line is actually not an image defect, it's a slit. And it's the entrance slit to the spectrograph part of the instrument, where you can then use the image for context, but then get a full spectrum of that black line to understand exactly what's going on. And what that allows you to do in turn is to see, in these graphs on the right-hand side, you see these emission lines, and you'll see them shift around. And that shifting is from the Doppler shift of the plasma moving towards you or away from you. What you can do with this is diagnose sort of a 3D version of what's happening. So on the left is the context image, on the right are the spectra. And of course, you have to anchor all this with models. The heliophysics, our understanding of it is driven by models. We theorize how things are supposed to work, and we put that to the test with this simulation. So this is a complete numerical simulation of the coronal mass ejection. And it takes a lot of time to compute. A lot of times you can use machine learning to take numerical shortcuts to make something like this compute hours rather than weeks. But the point is the models really anchor or are anchored by the observations. And the models tell you, well, what we should be looking for next. What are the key spatial, spectral, and temporal characteristics that would be most revealing of the underlying physics. And so this is where we go to a double zoom in. The mission we're working on now, the multi-slit solar explorer, or MUSE. So MUSE is sort of a super iris. And the thing we learned from iris is that it takes a while to observe the spectra. And in the time that it takes to go observe different locations, by the time you come back to when you started, stuff has already happened. It's completely different. So the time scale of the observations have to speed it up. And that's what MUSE is all about. It has a spectrograph with 35 slits instead of 1. So what that allows you to do is instead of scanning that single slit across the scene and then coming back to the beginning, you scan 35 of them all together. So you just do this, and then you don't have to go as far. You come right back to the beginning. You scan, therefore revisit the scene much more frequently. And it also has a higher spatial resolution. So here's an example of a single slit scan of something dynamic that's happening. Mass ejection at a pretty cool resolution. It kind of makes a mess, right? When things are moving on you, it's sort of like taking a picture while your dog is jumping. It can look weird. So this is what MUSE will do. And you see the left is the truth. The middle panel is how you see it using the multiple slits, which allow you very fast to revisit. And the right panel is with a single slit. What would happen if you could only image this with a single slit and have it play it again here. So you can see the middle panel, which is what MUSE will measure, looks a lot more like truth on the left than it does this this big mess of distorted dog. Right. So that's what we're driving at. I'll pivot quickly to weather and earth science. So now we are turning our gaze, by the way, back down to Earth. And so we have a lot of history here, specifically in Earth weather. So weather is a big deal. There are a lot of economic impacts of weather, severe weather. There's a lot of disasters. The numbers are enormous, right? And the small print that you can't read here says 27 separate billion-dollar weather disasters in 2024, and it's only getting worse. So we have to keep a really close eye on this, and that's why we have GOES. GOES is operated by the National Oceanic and Atmospheric Administration, NOAA, specifically NESDIS, the satellite division of NOAA, and it's used by the National Weather Service to forecast weather here on Earth and also in space. So as Allison mentioned, the solar instruments, they diagnose the heliophysics questions and answer the physical, scientific questions of what's going on in the sun. But then there's application of that for space weather, where we can now forecast and predict what the impacts would be. The sun, for example, throws out a big eruption. Where's that going to go? Is it going to hit the Earth? Is it going to disrupt our power grids, our communications, our GPS? Is it going to hurt the astronauts on the space station? These are all questions that are important. And of course, on the ground, we have severe weather monitoring and warning, specifically the lightning mapper, which I'll talk to you about next. So this is GLM, Geostationary Lightning Mapper. It's been in orbit since 2016. There's 2 of them watching over you every day around the clock. And what it is, it's a camera that takes 500 images of the Earth every second. And through that process, it's able to tell, by monitoring each pixel individually, whether there was a blip of light. And it measures over 1 million flashes of lightning every day across the hemisphere. So you can see a few pictures here. On the bottom right, you have the Falcon Heavy rocket. So it's the business end of the rocket that launched GOES-U just this, let's see, a little bit more than a year ago, summer of 2024. That was the last of 4 in the series. And the GLM is, there it is, right here. So you can see, Mike shown here, Mark, excuse me, shown here for scale. It's about 5 foot tall instrument, so it's this big here, and that means the entire satellite's about the size of a small bus. Pretty big beast. So how's it used? You can see the map up there. This is the map of the United States of weather. The U.S. is, the continental U.S. is divided into these smaller regions known as weather forecast offices. You're currently sitting in Monterey weather forecast region. And each of these WFOs has on-staff meteorologists who constantly monitor streams of data coming in from radar and satellite and kinds of other sensors, and then make forecasts. And it's not a thing where they sit around and take their sweet time and issue a forecast for tomorrow. Let's do it 6 p.m. or something. Sometimes they're really in hot seat. There's severe weather, severe. So that's a map of lightning flash rates. When it's red, it means the flash rate is extreme. It's a very severe thunderstorm. There may be a tornado associated with it. And you can see the little polygons that are drawn in the path of these thunderstorms. The yellow polygons